Hello there, and welcome to Science for Sleep, a space where curiosity drifts gently into calm, and science meanders slowly, letting your mind stretch its wings as it settles into rest. Tonight, we're embarking on a journey toward one of the most enormous stars visible from Earth, a red giant whose sheer scale is almost impossible to grasp, yet whose presence in the night sky has quietly fascinated humans for centuries. That star is Betelgeuse, perched in the shoulder of Orion, twinkling softly across countless light years, inviting us to wonder just how big something can be. You might glance at the sky tonight, find Orion rising, and there it is, a warm, reddish glow. Its size, its distance, its life, all of it beyond our ordinary experience, yet somehow present to us in that gentle shimmer, carrying the secrets of the cosmos right to your eyes. Have you ever paused on a chilly evening, tracing the familiar shape of Orion, and considered the scale of the stars you see? Betelgeuse isn't just a point of light. It's a massive, searing sphere of gas, hundreds of times wider than our Sun, so enormous that if it replaced the Sun, it would engulf Mercury, Venus, Earth, and reach well past Mars. And yet, it feels so small, distant, almost intimate when we observe it from our quiet corner of the universe. Tonight, we'll explore its size, its life, and its presence in the cosmos, all while letting your mind wander slowly through the space it occupies, stretching your imagination as gently as a cloud drifting across a twilight sky. If you find this kind of exploration soothing, or simply a pleasant pause from the day's busyness, I'd be ever so grateful if you liked the video and maybe subscribed, helping this quiet corner of curiosity reach others who might enjoy drifting with science in the same calm way. There's no rush here, no deadlines, no urgency, just the gentle unfolding of the story of a star, how it lives, how it shines, and how enormous it truly is. Perhaps you're lying in bed, maybe seated in a dimly lit room, or even curled up by a window that frames the night sky. Wherever you are, consider this an invitation to slow down and float alongside Betelgeuse for a while, letting its scale, its warmth, and its life resonate softly in your mind. Now, when we talk about the size of Betelgeuse, it's important to realize that size is not a simple number. It's something astronomers have measured using multiple methods, and yet each approach carries a quiet uncertainty. Distances in space are challenging to measure, especially when a star's edges are not sharply defined, when it swells and contracts slightly, and when clouds of gas and dust drift across our view. But from what we know, Betelgeuse is a star of staggering proportions. Its radius is roughly 700 times that of the Sun, its volume millions of times greater, and its surface area so vast that the Earth could fit inside it countless times over. Even more fascinating is how dynamic this size is. Betelgeuse is a variable star, expanding and contracting over periods of months and years. Its brightness fluctuates gently, sometimes dimming noticeably before returning to a stronger glow. This variability, subtle though it may seem from Earth, tells us that the star is alive in a sense, moving, pulsing, and breathing through the immense forces within it. As we start this journey, consider the contrast between what we see and what is. To the naked eye, Betelgeuse is just a red dot in the constellation of Orion. Yet, when we measure it with telescopes and interferometry, we find that this dot represents a star so massive and so wide that imagining it in human terms stretches the mind. If we were to replace our Sun with Betelgeuse, the inner planets would be swallowed and Earth itself would be engulfed. Yet even this comparison barely conveys the scale. The vast emptiness around it, the space it occupies relative to the nearest stars, and the light it emits all remind us that cosmic distances and sizes defy our usual ways of thinking. It is humbling to consider that the light we see from Betelgeuse tonight began its journey hundreds of years ago, The star we observe is already centuries old by the time its photons reach our eyes. In that sense, we're always seeing the past when we look at the sky. And because Betelgeuse is so far away, about 700 light years from Earth, we are witnessing the state of the star as it was long before our own lifetimes began. Some of the changes we see now may have occurred long ago, and some events in the star's life may be happening right now, completely invisible to us until their light eventually drifts across the expanse of space and reaches our gaze. This adds a quiet, reflective layer to our consideration of its size. It is not merely a physical measurement, but a temporal journey, a story unfolding slowly across centuries and carried by the light itself. Astronomers have developed ingenious ways to measure such distant giants. Techniques like stellar interferometry allow scientists to combine light from multiple telescopes to achieve resolutions far beyond what a single telescope could provide. Through these observations, we can infer the star's angular diameter, and then, knowing the distance, estimate its true physical size. In addition, modelling the star's brightness and spectrum allows astronomers to make educated calculations about the temperature, luminosity, and radius of the star. Every measurement, however precise, is a reminder of the vastness of space and the limits of human observation. Each time we refine our instruments, our understanding grows, yet we are still seeing only a fraction of what Betelgeuse truly is. And yet, there's an intimacy to this exploration. We often think of stars as distant, unapproachable, but observing Betelgeuse is a bridge between the enormous and the familiar. Its size and brightness are understandable when framed with comparisons to the sun, planets, and distances we can imagine. It pulses in a rhythm, it dims, it brightens, and it tells us about the forces at work in the hearts of massive stars. Thinking of its convection cells, which are enormous compared to anything on Earth, or the shock waves rippling across its surface, gives a sense of movement and life. Even in its massive, almost static appearance, there is motion, a constant evolution that stretches across decades and centuries. You might wonder, how does it feel to consider such scales? Does your mind reel at the enormity, or does it settle into a kind of quiet awe? This is part of the experience, part of why we slow down for the night and drift gently into contemplation. Science, in this way, becomes not just information but a meditation, a means to experience wonder without rushing, without pressing for immediate understanding. And as we let our thoughts drift along with the star, we begin to notice patterns in its variability, subtle flickers, small dimming events, all of which hint at processes occurring deep within its core. Betelgeuse is also a reminder of the impermanence of even the most massive things. It is nearing the end of its life as a red supergiant, a phase that will eventually culminate in a supernova, a violent yet beautiful transformation that will briefly outshine an entire galaxy. Considering this, the star's size takes on a new dimension. It is not just vast in space, but also fleeting in time, a cosmic monument to both magnitude and mortality. In observing it tonight, we are witnessing a star on the brink of change, enormous in scale yet subject to the same inexorable forces that govern all matter in the universe. So as we settle into this gentle exploration, imagine floating slowly through Orion, past its belt, past the faint glow of distant stars, and coming upon Betelgeuse. Its red-orange hue warms the darkness around it. You can sense its size not in literal measurement, but in the way it commands attention, in the light that reaches across centuries, and in the curiosity it sparks within you. What would it be like to stand upon a planet orbiting it, seeing the sun replaced by this immense sphere? How would the sky look, the seasons change, the days feel? These reflections are part of the journey, letting the mind wander safely while the body rests, carrying us gently from Earth to the outskirts of Orion's constellation, where imagination and science merge. Betelgeuse is not just a distant star, it is a story, a measure of scale, a pulse of energy and motion stretching across the galaxy. Its size invites humility, its light invites reflection, and its life invites us to consider not just how vast the universe is, but how interconnected we are to the cosmos we observe. And as we continue, we will explore its structure, its surface, its variability, and the subtle clues it offers about the life of stars, all without rushing, letting the knowledge settle slowly, like starlight drifting through the night and into the quiet corners of our minds. Every flicker of Betelgeuse is a whisper of physics, a trace of nuclear fusion, a rhythm of gravity, and a testament to the forces that build and destroy in the universe. Observing its scale helps us understand not only its size, but also the incredible energy it radiates, the processes shaping its outer layers, and the delicate balance keeping it from collapsing under its own mass. Each of these observations adds a layer to our understanding, a gentle unfolding that blends scientific discovery with quiet reflection. And so, as we prepare to look more closely at how astronomers measure it, how its brightness changes, and how its life cycle unfolds, take a slow breath. Allow your mind to settle into the vastness of space and notice the red-orange glow of Betelgeuse in your imagination, as real and as present as the world around you. Where are you watching from tonight? What part of your sky hosts this giant? While your body may be here, your mind is travelling across light years, drifting past planets, across solar winds, and toward the heart of a red supergiant that has existed long before you were born and will continue long after. Here begins our gentle voyage toward understanding not only the size of Betelgeuse, but also what it means for us as observers, thinkers, and dreamers, stretching our perspective beyond Earth, beyond the Sun, and toward a star so big it challenges the limits of our imagination. As we shift our gaze from the gentle contemplation of Betelgeuse's immense size to its presence in the night sky, let's imagine stepping outside just after dusk. The air is cool, maybe carrying the faint scent of evening grass or the soft hint of wood smoke. Above, the stars begin to appear one by one, tiny pinpricks of light scattered across a deepening blue canvas. Orion starts to take shape, a constellation familiar to many, yet always striking in its clarity. If you've ever traced its outlines with your eyes, you might notice the three stars forming the belt, lined up neatly like a row of celestial beads, and then, slightly offset, the bright reddish glow marking Betelgeuse on Orion's shoulder. The first thing you might notice is the colour. Most stars we see with the naked eye shine white or pale yellow, gentle and steady. But Betelgeuse radiates a warm red orange, a hue that feels almost tactile, like holding a glowing ember at arm's length. It's the kind of colour that draws your attention without needing brightness to compete. Even among the other stars in Orion, its warmth sets it apart. In fact, this colour is a clue to the star's surface temperature. Unlike our Sun, which burns at around 5,500 degrees Celsius, Betelgeuse's cooler surface, roughly 3,500 degrees, gives it this distinctive red-orange glow. It's fascinating to think that by simply noticing colour, even from hundreds of light years away, we are sensing the heat of an enormous sphere of gas and plasma, a star alive in motion and energy. Finding Betelgeuse isn't difficult if Orion is visible. Look for the belt first. The three stars, Alnitak, Alnilam and Mintaka, form a nearly straight line, easy to spot even in moderately light-polluted skies. From there, imagine Orion's outline, a hunter frozen in time. Betelgeuse forms the right shoulder if you picture Orion facing you. Across from it, Rigel marks the opposite foot, shining in a brilliant blue-white, almost a visual counterpoint. The contrast between the two is subtle but profound, a dance of colour and size that hints at the diversity of stars. Rigel is hotter, younger, and more massive in some ways, yet Betelgeuse dominates our imagination because of its size and its reddish, commanding presence. Even without a telescope, you can get a sense of its prominence by simply comparing it to the other stars in Orion. While the belt stars are precise and bright, Betelgeuse feels more substantial, as though it carries weight in the sky. This perception is partly physical and partly psychological. The human eye is sensitive to subtle colour differences, and our brains unconsciously note the star's steadiness, its position, and its hue, giving it a presence that feels almost tangible. Imagine for a moment that each flicker you see is a wave of energy that left the star decades or even centuries ago. Every photon that reaches your eyes carries information about Betelgeuse's state long before we were even born, a cosmic message written in red light. Once you have located Betelgeuse, it can be helpful to observe it over multiple nights. Its brightness is not fixed, and you might notice subtle changes that are invisible to casual observers. These variations, called semi-regular variability, occur as the star pulsates gently, expanding and contracting over periods ranging from hundreds to thousands of days. During certain times, the star's light can appear slightly dimmer or brighter. In late 2019 and early 2020, Betelgeuse entered an unusual dimming phase, so pronounced that even casual skywatchers could notice it without instruments. This event prompted excitement, speculation, and careful observation worldwide, as astronomers worked to determine whether the star was approaching a supernova or simply experiencing surface activity and dust ejection. By observing Betelgeuse regularly, even with modest equipment, you become part of a global effort to monitor the life of a red giant, connecting human curiosity across generations. For those with binoculars or small telescopes, Betelgeuse reveals even more subtle traits. Its disk is not resolvable in most amateur instruments, but careful observation shows slight variations in intensity across its surface. Modern interferometry has allowed scientists to image Betelgeuse directly, revealing a surface mottled with gigantic convection cells, each one larger than our Sun. The swirling, roiling motions of plasma are not static. They shift, creating patterns of light and dark that alter how the star appears to us on Earth. When we spot Betelgeuse in the night sky, we are glimpsing the outer shell of a living, breathing star, its surface dancing in complex motions governed by physics on a scale that defies ordinary imagination. Its place in Orion also makes Betelgeuse a useful marker for understanding stellar distances and movements. For centuries, astronomers have used constellations like Orion as reference points, charting positions of stars to track proper motion and distance. Even without sophisticated instruments, early skywatchers noted Betelgeuse's brightness, its reddish hue, and its position relative to nearby stars, building a record that modern scientists can compare against precise measurements. This continuity highlights a quiet human connection across centuries, as our ancestors also gazed upward, contemplating the same star, perhaps drawing stories and myths around it. Speaking of stories, Betelgeuse has long inspired imagination and cultural significance. In ancient times, its reddish colour was sometimes associated with fire, strength, or war. Mythologies across different cultures included Orion as a hunter or warrior, with Betelgeuse marking a crucial part of his form, a shoulder bearing weight and authority. Even today, storytellers and artists find inspiration in the star, weaving its light into fiction, poetry, and visual arts. Observing Betelgeuse becomes not just an astronomical exercise, but a quiet participation in a human tradition of wonder and reflection. If you step back, the act of spotting the star also invites contemplation of scale. Its apparent size in the night sky is minuscule, barely a point of light, yet in reality, it stretches across hundreds of millions of kilometers. Our human perspective compresses cosmic distances into something we can perceive visually, reminding us that appearances can be misleading, and understanding the universe requires patient measurement, reflection, and imagination. This contrast between what is seen and what exists offers a gentle lesson in humility, a reminder that there is always more beyond what our senses can detect directly. Moreover, observing Betelgeuse encourages patience, nights of watching the sky unfold slowly, tracing Orion, following the star's subtle shifts, all help attune the mind to the rhythms of the cosmos. Unlike digital screens or rapid streams of information, stargazing is quiet, continuous, and immersive. It teaches the kind of mindfulness that blends observation with reflection, that lets you drift along with the stars while noticing the small shifts in light and colour that signal vast processes beyond our immediate perception. In some ways, Betelgeuse serves as a gateway. By learning to spot it, you also start noticing the context around it. The 3 stars of Orion's belt, the faint glow of nearby nebulae, the relative brightness of Rigel, and the intricate patterns formed by surrounding constellations. Each observation connects you to a larger network of stars, distances, and histories. The sky is not static. It is a dynamic system where stars are born, live and die, and by following Betelgeuse, you are quietly witnessing one thread of that vast cosmic tapestry. Even in moments of casual observation, there are subtle cues to the star's immense physical presence. Its light, warm and steady, reaches Earth across hundreds of years, illuminating the night with energy produced by nuclear fusion at its core. The photons that touch your eyes tonight were generated by reactions deep within a sphere hundreds of millions of kilometers wide, travelling through empty space to arrive precisely now. Contemplating this journey, one begins to appreciate the interplay between distance, time, and energy that makes even simple stargazing a profoundly cosmic experience. As we continue, it is worth reflecting on the simplicity of the experience. You don't need advanced instruments to feel the wonder of Betelgeuse. Its colour, position and brightness are enough to anchor your attention, to provide a sense of scale and connection. The act of observing the star, quietly, without rush, is itself a gentle exploration. And for those who do choose to use telescopes or modern imaging techniques, each additional layer of detail only deepens the appreciation, revealing the complex physics, convective motions, and subtle pulsations that characterize this enormous red giant. Finally, the night sky, Orion and Betelgeuse offer more than measurements or scientific facts. They provide a frame for reflection, a rhythm that mirrors the slow unfolding of our own thoughts. When you locate Betelgeuse, notice its warmth, its steady glow, and its distant yet intimate presence. Allow yourself to linger there, tracing Orion, imagining the immense size of the star, thinking about the light years it has travelled, and letting the mind drift gently with the flow of the universe. This is the beginning of understanding not only how to spot the star, but also how to relate to it, to feel its scale, and to place ourselves in the cosmos in a way that is patient, calm, and contemplative. By observing Betelgeuse night after night, you begin to form a quiet companionship with it, noticing its changes, following its patterns, and connecting to a process that unfolds over centuries. Each flicker, each subtle shift in brightness, is a reminder that even something so enormous has variability, rhythm, and life. As your eyes linger on the glow of Betelgeuse tonight, it helps to pause and reflect on what makes this star truly exceptional. Many stars dot the night sky, some dim, some brilliant, but few capture attention in the same way. Betelgeuse is not just bright, it is enormous, old, and alive with energy in ways that are difficult to fully grasp. While we might see it as a small point of red-orange light, the reality is that Betelgeuse is a supergiant, a star whose size and character place it in a class of its own. The mind can struggle to imagine its scale, so perhaps we begin with a gentle comparison. Consider our sun, warm and familiar, a sphere of light that nurtures life and dictates the rhythms of our days. Betelgeuse dwarfs it. If the sun were a modest beach ball resting on the grass, Betelgeuse would be a colossal sphere large enough to engulf the entire neighbourhood. Its radius stretches approximately 700 times that of the Sun. Imagine the Earth itself orbiting within the boundaries of this star. The planet would be lost in its fiery surface, along with Mercury, Venus, and even Mars. Yet despite its vastness, Betelgeuse remains a single, cohesive star, bound together by gravity, nuclear fusion, and a delicate balance that allows it to exist in this state for millions of years. Its sheer scale also changes how we perceive it relative to other stars. Most stars we observe are smaller, main-sequence stars burning steadily like our Sun. Betelgeuse is in a late stage of stellar evolution, a red supergiant approaching the end of its life. That means it has exhausted the hydrogen fuel at its core and has expanded outward, swelling to hundreds of times its original size. It is a star in transformation, a reminder that nothing in the cosmos remains static forever. Its appearance, colour, and brightness are all clues to this evolutionary stage. The red-orange glow tells us the surface has cooled compared to its earlier life, while the enormous size speaks of the expansion caused by internal processes and nuclear reactions pushing outward against gravity's pull. What makes Betelgeuse unlike any other is not just its size, but its variability. It is a semi-regular variable star, meaning its brightness changes over time. Sometimes these changes are subtle, barely perceptible to the naked eye, while at other times they are dramatic, such as the Great Dimming between late 2019 and early 2020. During this period, Betelgeuse's light decreased by more than a third, prompting astronomers and skywatchers alike to pause and wonder if the star was on the brink of exploding. While the exact cause was later attributed to a combination of surface activity and dust ejection, the event highlighted that Betelgeuse is alive in ways that make observing it a dynamic experience. Its variability, combined with its size and colour, creates a presence that feels intimate, as though we are watching a living being, pulsating and breathing across the void. The internal workings of Betelgeuse further set it apart. Inside, the star hosts enormous convection cells, massive regions where hot gas rises, cools and sinks back down, similar to the boiling motions of a pot of water, but on scales so immense they dwarf our entire solar system. These cells create mottled patterns across the star's surface, regions that are brighter or darker, constantly shifting as energy moves outward. This dynamic surface contributes to the subtle flickering we observe from Earth. Even though the star appears as a steady point of light, the reality is a turbulent, restless sphere of plasma, constantly rearranging itself in ways both predictable and surprising. Betelgeuse also challenges our notions of time. Its immense size means that changes on its surface unfold over months or years, yet we perceive them in a single moment when we look skyward. Its light, travelling roughly 700 years to reach Earth, connects us to the star's past. In a sense, we are always looking backward in time, observing events that happened centuries ago. Every pulse, every dimming, every flicker we detect today is a record of processes that occurred long before we were born. This combination of vast scale, temporal distance and dynamic variability makes Betelgeuse both a scientific marvel and a profound object of reflection. The star's uniqueness extends beyond its physical properties into the human experience of observing it. Its position in Orion has made it a fixture of mythology, navigation, and cultural storytelling. Across civilizations, Betelgeuse has inspired myths, symbolized warriors, fire or change, and even guided travellers across deserts and seas. Its red glow has been noted and admired by skywatchers for centuries, a constant yet evolving presence in the night sky. When we observe it now, we are participating in a tradition that spans generations, connecting our awareness of the cosmos to those who looked up long before telescopes and photography existed. To truly appreciate why Betelgeuse is unlike any other, we can also consider its mass. It is estimated to be around 20 times the mass of the Sun, concentrated into a volume that dwarfs our own planetary system. This mass drives the star's evolution, influencing the nuclear reactions at its core and the expansion of its outer layers. The balance between gravity pulling inward and pressure pushing outward from fusion is delicate. Even slight changes can lead to dramatic consequences over astronomical timescales. In this sense, Betelgeuse is a star teetering on the edge, massive and luminous yet fragile in the cosmic sense. Its impending fate as a supernova further distinguishes it. While stars like our Sun will quietly fade into white dwarfs over billions of years, Betelgeuse's end will be spectacular. One day, in the not-too-distant cosmic future, it will explode, releasing enormous energy and dispersing heavy elements across space. This event will briefly make Betelgeuse visible during the day, an extraordinary demonstration of the life cycle of massive stars. The knowledge that we are observing a star in the last stages of its life adds depth to our contemplation, reminding us that size and power do not equate to permanence. Even the way we measure Betelgeuse's size underscores its distinctiveness. Unlike smaller stars, whose diameters are easier to infer through brightness and distance, Betelgeuse has an irregular shape due to convection, rotation, and pulsations. This means that its edge is not perfectly spherical, and its diameter can vary over time. Modern techniques like interferometry and adaptive optics allow astronomers to resolve its disk and even detect surface features. These measurements provide both data and wonder, showing us that the star is not a simple sphere, but a complex evolving object with a personality expressed in light, heat, and motion. Perhaps what is most remarkable is how Betelgeuse reminds us of the limits of our perception. To the naked eye, it is merely a bright dot in Orion, a point of reference in a familiar constellation. Yet, when we layer scientific observation, historical context, and imaginative reflection, it becomes a massive, pulsating, ancient giant, challenging our understanding of scale, time, and energy. The star exists simultaneously as a distant object, a historical witness, and a tangible presence in our night sky. Its red glow carries with it both physical reality and human meaning, bridging the gap between cosmic distance and personal observation. By observing Betelgeuse, we also become aware of the variety of stars that populate the galaxy. Not all stars are the same, and the more massive ones, like Betelgeuse, live fast and end spectacularly. In contrast, smaller stars burn steadily for billions of years, their light comforting yet less dramatic. The diversity of stellar life cycles reminds us that the universe is both orderly and varied, that even among the vast numbers of stars, each has a story, a rhythm and characteristics that set it apart. Betelgeuse, with its size, variability, and impending fate, occupies a special place, both scientifically and emotionally, in our understanding of the cosmos. Its surface is also a laboratory of extremes. Temperatures at the core reach tens of millions of degrees, driving nuclear fusion that produces the energy radiated into space. The outer layers, cooler and expanding, generate the red glow we see. Convection cells rise and fall, sending gas and plasma surging across thousands of millions of kilometers. The interplay of pressure, gravity, and energy produces pulsations that ripple across the star's atmosphere, changing its brightness in ways we can detect from Earth. This complexity is part of what makes Betelgeuse unlike any other star we can observe directly. Even the dimming events add layers to its uniqueness. The Great Dimming of 2019 to 2020 revealed that clouds of dust ejected from the star's surface can temporarily obscure its light, creating dramatic changes in appearance. These events are rare among observable red supergiants and highlight the interplay of stellar activity, surface convection, and surrounding material. When we witness such phenomena, even through images or careful notes, we are watching a living star, one whose scale and behaviour are dynamic and ever-changing. In a broader sense, Betelgeuse challenges our human perspective on size and distance. We are accustomed to measuring and comparing objects on Earth, where a mountain or an ocean feels enormous. Yet here is a star whose diameter is hundreds of times larger than the Sun's, whose light has travelled centuries to reach us, and whose internal processes span vast distances and timescales. Observing it reminds us that scale is relative, and that the cosmos operates on dimensions far beyond our immediate intuition. Even with modern technology, Betelgeuse remains partly mysterious. Its irregular shape, surface turbulence and variability all complicate precise measurements. Astronomers continue to refine models, using interferometry, spectroscopy and computer simulations to understand its mass, radius and behaviour. Each observation adds a small piece to the puzzle, yet the star retains an air of unpredictability, a gentle reminder that the universe is vast, complex and often surprising. So, as you trace its reddish glow across Orion tonight, remember that Betelgeuse is more than just a dot in the sky. It is enormous, dynamic, variable and ancient. It is a star alive with energy, a celestial neighbour whose size stretches comprehension and whose light connects centuries. It is a reminder that the night sky, while seemingly static, is filled with objects of complexity and wonder, each with its own story, scale and rhythm. By spending these moments with Betelgeuse, observing its colour, its position, and its subtle flickers, we begin to feel the enormity of space and time. We gain an appreciation not only for the star itself, but for the processes that govern the lives of massive stars. We witness the interplay of energy, gravity and matter on a scale that challenges human intuition, and we begin to understand why astronomers and skywatchers alike describe Betelgeuse as a star unlike any other. Its presence in Orion, its brightness, its size and its variability all combine to create an experience that is both scientific and meditative. Looking at Betelgeuse, we are reminded of our own smallness, our place in the cosmos, and the ways in which observation and imagination can expand our perception. From quietly noticing Betelgeuse glowing in Orion and reflecting on how unusual it is, the next natural step is to ask a question that sounds simple at first, yet becomes surprisingly intricate the longer you sit with it. How do we actually measure something like this? Not just in a general sense, but in a way that turns that tiny reddish point in the sky into a number, a size, a distance, something we can compare to the Sun, to our solar system, to anything familiar at all. It might seem like astronomers simply point a telescope, take a picture, and read off a value. But when it comes to a star like Betelgeuse, things are rarely that straightforward. Unlike a planet or a nearby object, Betelgeuse is so far away that even our most powerful telescopes struggle to resolve it clearly. Its edges are not sharp, its surface is not uniform, and its light has travelled hundreds of years to reach us, carrying with it subtle distortions and uncertainties. Measuring a cosmic giant, as it turns out, is a bit like trying to determine the size of a softly glowing cloud from across a vast valley, using only the faint light that reaches your eyes. To begin with, astronomers need to know two key things: how big the star appears from Earth and how far away it is. These two pieces of information work together, like ingredients in a recipe. If you know how large something looks and how far away it sits, you can calculate its true size. This sounds simple, but each of those measurements comes with its own set of challenges. Let's start with how large Betelgeuse appears in the sky. When you look at it with your eyes, it appears as a point of light, no different in shape from any other star. Even through most telescopes, it remains a tiny dot. But with advanced techniques, astronomers can measure something called its angular diameter, which is essentially how wide the star appears from our point of view, measured in very small units called arcseconds. To give a sense of scale, an arcsecond is 1/3600th of a degree, and Betelgeuse's apparent size is measured in fractions of that. It's incredibly small, far beyond what our eyes can distinguish. So how do scientists measure something so tiny? This is where a clever method called interferometry comes into play. Instead of relying on a single telescope, astronomers combine the light collected by multiple telescopes spread across large distances. By doing this, they effectively create a telescope as large as the distance between them. The greater the separation, the finer the detail they can resolve. Imagine trying to read a distant sign. One eye might struggle, but if you could somehow merge the perspectives of two eyes placed far apart, your ability to detect detail would improve dramatically. Interferometry works on a similar principle, except instead of eyes, we're using telescopes, and instead of a sign, we're observing a star hundreds of light years away. Using this technique, astronomers have been able to measure Betelgeuse's angular diameter with remarkable precision. They can even detect that its surface is not perfectly uniform, that it has brighter and darker regions, and that its shape can appear slightly irregular due to its turbulent atmosphere. But knowing how large it looks is only half the story. The other half is distance, and this is where things become even more delicate. Measuring the distance to stars is one of the oldest challenges in astronomy. For nearby stars, scientists use a method called parallax. This involves observing how a star appears to shift slightly against the background of more distant stars as Earth moves around the Sun. By measuring this tiny shift, astronomers can calculate how far away the star is. It's a bit like holding your finger in front of your face and closing one eye, then the other. Your finger seems to move relative to the background. The closer your finger is, the more it appears to shift. The same principle applies to stars, though the shifts are incredibly small, requiring precise instruments to detect. For Betelgeuse, parallax measurements have been made using space-based observatories like the Hipparcos and later the Gaia. These missions are designed to map the positions and distances of stars with extraordinary accuracy. Even so, Betelgeuse presents a challenge. Its surface is not stable, and its outer layers can shift and expand, making it harder to pinpoint its exact center. This introduces a level of uncertainty into distance measurements. Depending on the data and methods used, estimates for its distance have varied, though they generally place it around 500 to 700 light years away. Now, when you combine the angular diameter with the distance, you can calculate the star's actual size, and this is where the numbers begin to stretch the imagination. Using current estimates, Betelgeuse's radius is roughly 600 to 900 times that of the Sun. That means its diameter could be over 1 billion kilometers. To put that into perspective, if Betelgeuse were placed at the center of our solar system, its outer layers would extend beyond the orbit of Mars, and in some estimates, even approach Jupiter. But even this comparison has to be handled gently, because Betelgeuse does not have a solid surface. Its outer layers are diffuse, gradually fading into space. There isn't a sharp boundary where the star ends and empty space begins. Instead, astronomers define its surface based on where the light we observe is emitted, which can shift depending on wavelength and observational method. So when we say Betelgeuse is a certain size, we are really describing a region, a zone of glowing gas rather than a solid edge. It's a bit like trying to define the edge of a flame. You can see where it's brightest, but the outer wisps fade gradually, making the exact boundary difficult to pin down. Another layer of complexity comes from the fact that Betelgeuse is not constant in size. It pulses. Over time, it expands and contracts slightly, changing its radius by a noticeable amount. These pulsations are tied to processes deep within the star, where energy generated in the core moves outward, causing the outer layers to swell and then settle back again. This means that any measurement of its size is, in a sense, a snapshot. It captures the star at a particular moment in its cycle. If you measure it again months or years later, you might get a slightly different value. This variability is part of what makes Betelgeuse so fascinating, but it also means that its size is not a single fixed number. Astronomers also use spectroscopy to learn more about the star. By analysing the light it emits, they can determine its temperature, composition, and motion. This information helps refine models of the star's structure and behaviour, which in turn improves estimates of its size. Spectroscopy reveals that Betelgeuse is rich in elements produced through nuclear fusion, and that its outer layers are moving in complex patterns. Some regions are rising, others are falling, and the entire surface is in constant motion. These movements affect how light is emitted and can subtly influence measurements. There's also the matter of dust. Betelgeuse is known to shed material into space, creating clouds of gas and dust around it. These clouds can absorb and scatter light, making the star appear dimmer or altering its apparent size depending on the wavelength observed. During the Great Dimming event, for example, a cloud of dust ejected from the star temporarily obscured part of its surface, changing how it appeared from Earth. All of this means that measuring Betelgeuse is not a single task, but an ongoing process. Astronomers gather data from multiple sources, compare results, refine models, and gradually build a clearer picture. It's a quiet, patient effort, one that unfolds over years and decades. And yet, despite all these complexities, the results are remarkably consistent in one important sense. No matter how you measure it, no matter which method you use, Betelgeuse is enormous. It stands among the largest stars we can observe directly, a true giant in every sense of the word. What's interesting is how these measurements, precise as they are, still leave room for wonder. Even when we assign numbers, even when we calculate radii and distances, there remains a gap between the data and our intuition. 1 billion kilometers is a number we can write down, but not one we can easily feel. So perhaps it helps to return to simpler images. Imagine the sun, steady and bright, at the center of our solar system. Now imagine replacing it with Betelgeuse. The inner planets vanish inside it. Earth, gone. Mars, gone. The familiar layout of our cosmic neighborhood is swallowed by a vast glowing sphere. And yet, from here, from Earth, it remains a small, flickering point in the sky. That contrast between appearance and reality is at the heart of what makes measuring a star like Betelgeuse so compelling. As we continue to explore it, to refine our measurements and deepen our understanding, we're not just learning about a distant object. We're also learning about the tools and methods that allow us to reach across space, to turn faint light into knowledge, and to connect our small world to something unimaginably large. As those careful measurements begin to settle in your mind, turning a distant glow into something vast and almost tangible, it becomes interesting to step away from numbers for a moment and look at how long this star has been part of human awareness. Long before telescopes, long before interferometry, long before we had any way to calculate radii or light years, Betelgeuse was already there, quietly shining in the night sky, noticed, named, and woven into stories by people who had no idea just how enormous it truly was. Picture a clear night thousands of years ago. No artificial lights, no glowing screens, no hum of distant cities. Just darkness, deep and uninterrupted, with stars appearing brighter and more numerous than most of us ever see today. Orion would rise just as it does now, its familiar shape forming across the sky, and there, marking one shoulder of the hunter, a reddish star that stood out among the others. Even without instruments, that colour would have been noticeable. It's subtle, yes, but in a truly dark sky, Betelgeuse doesn't look quite like the rest. It has a warmth to it, a soft tint that distinguishes it from the sharper white points nearby. Early skywatchers didn't need to know about temperature or spectral classes to recognise that this star was different. They saw it with their eyes, and they remembered it. Across cultures, Orion became one of the most recognisable patterns in the sky. In ancient Greece, it was associated with a great hunter, a figure of strength and presence. Betelgeuse, positioned at the shoulder, naturally took on a role of importance within that figure. It wasn't just any star in the constellation. It was part of the body, part of the story, part of the identity. The name Betelgeuse itself has an interesting history. It comes from Arabic, from a phrase often translated as the hand of Orion or the armpit of Orion, depending on interpretation and historical transcription. Over time, through translation and copying, the name shifted into the form we use today. There's something quietly charming about that, the idea that a star's name can evolve over centuries, shaped by language, culture, and the small imperfections of human record-keeping. In the Islamic Golden Age, astronomers carefully catalogued stars, refining earlier Greek knowledge and adding their own observations. Betelgeuse was included in these records, its brightness and position noted with care. Without modern instruments, these astronomers relied on keen eyesight and systematic observation, tracking changes and preserving knowledge that would later feed into the development of modern astronomy. Meanwhile, in other parts of the world, Betelgeuse also found its place in local traditions. In some indigenous cultures, the stars of Orion were interpreted differently, forming figures and stories unique to each region. Betelgeuse, with its distinct colour, often carried special significance, sometimes associated with fire, with life, or with change. These interpretations varied, but they shared a common thread. This star stood out enough to be remembered and included in the sky's narrative. What's remarkable is that all of these observers, separated by geography and time, were looking at the same object we see today, the same light, travelling across centuries, reaching different eyes in different eras, carrying the same subtle red glow. The star itself was already ancient then, already nearing the later stages of its life, yet from a human perspective it appeared constant, reliable, part of the unchanging backdrop of the night. Of course, it isn't truly unchanging, and this is where things become especially interesting. There are historical records suggesting that Betelgeuse's brightness may have varied noticeably, even before modern astronomy. Some ancient descriptions imply that it was once considered among the brightest stars in the sky, perhaps even rivaling others more strongly than it does today. While these accounts are difficult to interpret with precision, they hint at something we now know to be true. Betelgeuse is variable. It doesn't shine with a perfectly steady intensity. Instead, it brightens and dims over time, following cycles that can span months or years. To a casual observer, these changes are subtle, easy to miss unless you're paying close attention. But to someone who watches the sky regularly, who becomes familiar with the relative brightness of stars, those shifts can become noticeable. Imagine a skywatcher centuries ago, returning to the same patch of sky night after night, season after season. Over time, they might begin to notice that this reddish star isn't always quite the same. Sometimes it seems a little brighter, sometimes a little fainter. Without the language of stellar physics, without concepts like pulsation or convection, they might simply accept it as part of the star's nature, a quiet irregularity in an otherwise steady sky. That awareness, even without explanation, is a form of knowledge. It's observational, experiential, grounded in patience and attention. And in a way, it mirrors what astronomers still do today, though with more advanced tools. As time moved forward and telescopes entered the picture, Betelgeuse continued to reveal itself in new ways. Early telescopic observations confirmed its colour more clearly, showing that it was not just a trick of the eye but a genuine property of the star. Its brightness could be compared more precisely to neighbouring stars, and its variability could be tracked with greater confidence. By the 19th century, astronomers had begun to classify stars based on their spectra, analysing the light they emit to determine temperature and composition. Betelgeuse fell into the category of red stars cooler than the Sun, with a spectrum indicating a different stage of stellar life. This was one of the first steps toward understanding that not all stars are the same, that they evolve, that they change over time. In the 20th century, things accelerated. With the development of modern astrophysics, Betelgeuse became a subject of detailed study. Its size, its mass, its distance, all began to be measured with increasing accuracy. It was identified as a red supergiant, a massive star that had expanded dramatically after exhausting the hydrogen in its core. But even as the science advanced, the sense of continuity remained. The same star that ancient observers had watched was now being analysed with sophisticated instruments, yet it still appeared in the same place in the sky, still part of Orion, still glowing with that distinctive reddish hue. Then came moments like the Great Dimming, events that remind us that Betelgeuse is not just a static object, but a dynamic system. When its brightness dropped noticeably in 2019 and 2020, it captured global attention. People who had never looked up at Orion before suddenly became aware of this star, checking its brightness, comparing it to others, wondering what might happen next. For a brief period, Betelgeuse became part of a shared human experience, much like it had been in ancient times, though now connected by modern communication and scientific understanding. Observatories around the world turned their instruments toward it, gathering data, analysing light curves, modelling dust clouds, trying to understand what was unfolding. The conclusion that the dimming was caused by a combination of surface cooling and a cloud of dust ejected from the star added another layer to its story. It wasn't about to explode, at least not immediately, but it had reminded us that even the most familiar stars can surprise us. Looking back across these centuries, what stands out is not just the accumulation of knowledge, but the continuity of attention. Betelgeuse has been observed, named, described, and studied by countless people, each adding a small piece to the larger picture. From early skywatchers tracing constellations to modern astronomers analysing spectral lines, the thread of curiosity remains unbroken, and there's something quietly comforting in that. The idea that a star can connect generations, that the same point of light can be part of so many different lives, so many different moments. It suggests that while our tools and understanding change, the act of looking up, of noticing, of wondering stays the same. At the same time, our perspective has shifted dramatically. Where once Betelgeuse was simply a bright red star in a familiar pattern, it is now understood as a massive, evolving supergiant, hundreds of times larger than the Sun, nearing the end of its life. The stories we tell about it have changed, from mythological narratives to scientific models, but both are attempts to make sense of what we see. Even today, Betelgeuse continues to be monitored closely. Its variability, its surface activity, its potential future as a supernova, all make it a star of ongoing interest. Observations from ground-based telescopes and space missions provide a steady stream of data, refining our understanding and sometimes raising new questions. And yet, if you step outside tonight and look at Orion, none of that complexity is immediately visible. You'll see a red-orange star, steady and quiet, part of a familiar shape. The centuries of observation, the layers of knowledge, the intricate physics, all remain hidden behind that simple point of light. That contrast between simplicity and complexity is part of what makes Betelgeuse so compelling. It is both accessible and mysterious, both familiar and extraordinary. It invites you to look, to notice, to ask questions, and to follow those questions as far as you like, whether that leads into ancient stories or modern astrophysics. As that long thread of human observation settles into place, stretching from ancient sky watchers to modern telescopes, it becomes easier to shift our attention from how Betelgeuse has been seen to what it actually is going through right now. Because beneath that steady reddish glow lies a star that is no longer in its youth. It is, in a very real sense, an aging giant, moving through one of the final stages of its life. To understand what that means, it helps to begin with something more familiar. Our Sun, steady and reliable, is currently in what astronomers call the main sequence phase. This is the longest and most stable period in a star's life, where it fuses hydrogen into helium in its core, producing energy that balances the inward pull of gravity. That balance is what keeps the sun from collapsing or expanding uncontrollably. It's a quiet equilibrium, one that has lasted for billions of years and will continue for billions more. But stars like Betelgeuse don't follow quite the same timeline. From the very beginning, Betelgeuse was far more massive than the Sun, likely around 15 to 20 times its mass. And in the universe, mass changes everything. The more massive a star is, the more pressure builds up in its core, and the faster it burns through its nuclear fuel. So while the Sun can afford to burn slowly and steadily, Betelgeuse lived fast right from the start. You might imagine it like two candles, one small and steady, burning slowly through the night, the other large and intense, its flame brighter, hotter, but consuming its wax much more quickly. Betelgeuse is that second candle. In its early life, it would have been a blue-white star, extremely hot and luminous, radiating enormous amounts of energy. But that phase didn't last nearly as long as the Sun's current stage. Over millions of years rather than billions, Betelgeuse began to exhaust the hydrogen fuel in its core. And this is where things start to change. When the hydrogen in the core runs low, the balance between gravity and pressure begins to shift. Gravity, always pulling inward, starts to gain the upper hand. The core contracts slightly under its own weight, becoming hotter and denser. At the same time, the outer layers of the star respond by expanding outward. This expansion is not subtle. The star begins to swell, growing larger and larger, its outer layers stretching far into space. As it expands, those outer layers cool, and the star's colour shifts from blue-white to orange and eventually to red. This is how a star becomes a red giant, or in Betelgeuse's case, a red supergiant. And this is the phase we see today. Betelgeuse has expanded to such an extent that its radius is hundreds of times larger than the Sun's. Its surface temperature is lower than it once was, giving it that warm, reddish appearance. But inside, the story is far from calm. As the core contracts and heats up, new types of nuclear fusion begin. Instead of just hydrogen turning into helium, the star starts fusing helium into heavier elements like carbon and oxygen. In even later stages, more massive stars can go on to fuse elements like neon, silicon, and eventually iron. Each of these stages happens faster than the last. Hydrogen fusion might last millions of years, helium fusion perhaps hundreds of thousands. The later stages can be astonishingly brief on cosmic timescales, sometimes lasting only thousands or even hundreds of years. It's as though the star, having spent most of its life in a steady rhythm, suddenly begins to accelerate toward its final act. Meanwhile, the outer layers of Betelgeuse are anything but stable. Because the star is so large and its gravity is relatively weaker at the surface, those outer layers are loosely bound. They can rise and fall in enormous convection currents, creating vast cells of hot gas that move like slow, boiling currents across the star's surface. These cells are not small features. Each one can be comparable in size to our entire solar system. Imagine that for a moment. On the Sun, convection cells are relatively small compared to the star itself, but on Betelgeuse, a single rising plume of gas can span distances greater than the orbit of Earth. The surface is constantly shifting, bright regions forming and fading, darker patches appearing and disappearing. This contributes to the star's variability, the gentle changes in brightness that we can observe from Earth. It's not a steady, unchanging glow, but a dynamic, evolving surface, shaped by forces that operate on scales far beyond our everyday experience. Another consequence of this aging process is mass loss. Betelgeuse is shedding material into space, slowly but continuously. Streams of gas drift away from the star, forming a vast envelope around it. Sometimes larger events occur, where chunks of material are expelled more dramatically, creating clouds of dust that can obscure the star's light. This is likely what happened during the Great Dimming event. A large amount of material was ejected from the star's surface. cooled, and formed a cloud of dust that temporarily blocked some of its light from reaching us. From our perspective, the star appeared to fade, not because it had lost energy, but because something had come between us and its glowing surface. All of this is part of what it means for a star to grow old. It becomes larger, cooler on the outside, but more active within, more unstable, more dynamic. It begins to lose mass, to change more rapidly, to move through stages that bring it closer and closer to its final transformation. And for a star like Betelgeuse, that final transformation will be dramatic. Eventually, the core will build up elements that can no longer release energy through fusion. Iron in particular marks a kind of endpoint. Fusing iron does not produce energy. Instead, it consumes it. When the core becomes dominated by iron, the delicate balance between pressure and gravity can no longer be maintained. At that point, gravity wins. The core collapses in a fraction of a second, and the outer layers rebound in a powerful explosion. This is a supernova, one of the most energetic events in the universe. For a brief time, the star can outshine an entire galaxy, releasing as much energy in seconds as the sun will emit over its entire lifetime. Betelgeuse is expected to meet this fate someday, but someday in this context does not mean tomorrow or next year. It could be tens of thousands or even hundreds of thousands of years away. From a human perspective, that's effectively forever. From a cosmic perspective, it's the blink of an eye. Still, the fact that Betelgeuse is in this late stage means we are observing a star nearing the end of its life cycle. It has already passed through its youth, its stable adulthood, and is now in a phase of expansion, variability, and gradual transformation. There's something quietly profound about that. We are not just looking at a star as it is, but as it becomes something else. Every photon that reaches us carries information about a star in transition, a star that has already changed since that light began its journey. And yet, despite all this activity, all this complexity, the experience of observing Betelgeuse remains simple. You look up and there it is, and a reddish point of light, steady enough to feel familiar, subtle enough to feel calm. The vast processes unfolding within it are hidden from view, compressed into that single glow. This contrast between simplicity and complexity, between what we see and what is happening, is part of what makes the study of stars so compelling. It invites you to look deeper, to imagine the layers beneath the surface, to consider the immense forces at work in something that appears so quiet from afar. As you let that idea settle, the notion of Betelgeuse as an aging star begins to feel less abstract. It becomes a story, one that unfolds slowly, guided by physics, but experienced through observation and imagination. As that picture of an aging star begins to settle, with Betelgeuse expanding, shedding material, and moving through its later stages, it becomes natural to look a little more closely at what this transformation actually involves. Not just that the star has grown larger, but how it made that transition, how a once relatively compact, intensely hot star became something so vast that its outer layers stretch across distances we struggle to picture clearly. What we're seeing now, when we look at Betelgeuse, is the result of a profound shift in its internal structure. This isn't simply a star getting bigger in the way a balloon inflates. It's a complete reorganization of how energy moves through the star, how pressure balances gravity, and how the outer layers respond to changes deep within the core. Earlier in its life, Betelgeuse would have been much hotter and more compact, burning hydrogen in its core with remarkable intensity. That energy production created outward pressure, holding the star in a stable configuration. Gravity pulled inward, fusion pushed outward, and for a time those forces remained in balance. But once the hydrogen in the core began to run low, that balance shifted. The core, no longer able to sustain the same level of fusion, began to contract under its own gravity. As it did, it heated up. That increase in temperature allowed new fusion processes to begin, but not in the same place or in the same way as before. Instead of a single stable fusion region in the core, Betelgeuse developed multiple layers of fusion, almost like an onion, each shell producing energy from different elements. Hydrogen might still fuse in an outer shell, while helium burns deeper inside, and heavier elements begin forming even closer to the center. This layered structure is one of the defining characteristics of a supergiant star, and it changes everything about how the star behaves. As the core contracts and heats, the energy generated doesn't stay neatly contained. It begins to move outward, and the outer layers of the star respond by expanding dramatically. This expansion is not gentle or uniform. It is driven by immense forces, pushing the star's outer atmosphere outward into space, stretching it thinner and thinner as it grows. That's how Betelgeuse becomes a red supergiant. The word awakens here is not about the star becoming active for the first time, but about it entering a new phase where its presence becomes more pronounced, more dynamic, more noticeable even across vast distances. Its size increases so much that, despite its cooler surface, it remains one of the brightest stars in our sky. And that cooler surface is an important detail. As Betelgeuse expands, its outer layers spread out over a much larger volume. The energy produced in the core has more space to disperse, which means the surface temperature drops. That's why the star glows red-orange instead of blue-white. It's not that it has become less energetic overall, but that its energy is distributed differently. In a way, it's like spreading the same amount of warmth over a larger area. The intensity at any single point decreases, even though the total energy remains enormous. This shift in temperature and size also affects how energy moves through the star. In a smaller, hotter star like the Sun, energy travels outward primarily through radiation in certain regions, moving as photons that are absorbed and re-emitted countless times before reaching the surface. In Betelgeuse, however, convection plays a much larger role. Convection is the process where hot material rises, cools, and then sinks again, creating circulating currents. On Earth, you can see this in boiling water, where bubbles and currents move continuously. In Betelgeuse, these currents are not small or localized. They are enormous, spanning vast portions of the star's surface. Each convection cell can be so large that, if you placed it in our solar system, it would stretch across the distance between planets. These cells rise slowly, carrying energy from the interior toward the surface, then cool and sink back down, creating a constant churning motion. This gives the star a kind of slow, rhythmic activity. It's not chaotic in a violent sense, but it is constantly changing. Bright regions appear where hot material reaches the surface. Darker regions form where cooler material descends. Over time, these patterns shift, contributing to the variations in brightness that we can observe from Earth. Another aspect of this awakening is the star's atmosphere. Unlike the Sun, which has a relatively well-defined surface, Betelgeuse has an extended atmosphere that stretches far beyond what we might think of as its visible edge. This atmosphere is composed of gas that has been lifted from the star's surface, forming a kind of halo that surrounds it. In some regions, this material becomes dense enough to form dust. That dust can interact with the star's light, absorbing and scattering it, which can change how bright the star appears to us. It also means that Betelgeuse is actively contributing material to the surrounding space, enriching it with elements that will one day become part of new stars, planets, and perhaps even life. So when we talk about Betelgeuse as a supergiant, we're not just describing its size. We're describing a phase where the star is actively reshaping its environment, both internally and externally. There's also a sense in which this stage is temporary, though temporary here still spans immense periods of time compared to human experience. The red supergiant phase does not last as long as the earlier, more stable phases of a star's life. It is a period of transition, of increased activity, of structural complexity. The star is moving through stages more quickly now, burning different fuels, changing its internal configuration, preparing in a sense for what comes next. And yet, from our perspective, it appears steady. Night after night, Betelgeuse rises and sets, its reddish glow marking Orion's shoulder. The changes we describe, the convection, the pulsations, the mass loss, all unfold slowly enough that they blend into a sense of continuity. It takes careful observation, patience, and sometimes decades of data to notice the patterns. This contrast between internal activity and external calm is one of the most striking aspects of a supergiant star. It invites you to think about scale, not just in terms of size, but in terms of time. Processes that are rapid and intense within the star can still appear slow and gentle when viewed from Earth. The distances involved soften everything, turning dramatic changes into subtle variations. If you imagine being closer, much closer, the experience would be entirely different. Instead of a steady point of light, you would see a vast, glowing surface, shifting and moving, with enormous currents of gas rising and falling. The star would not feel calm at all. It would feel alive in a way that is difficult to describe, its surface constantly reshaping itself under the influence of forces we rarely encounter directly. But from here, from our quiet vantage point, all of that is condensed into a soft reddish glow, and that glow carries with it the story of a star that has grown, expanded, and entered a new phase of its existence. A phase where its size becomes truly extraordinary, where its structure becomes more complex, and where its future begins to take shape. It becomes easier to understand why Betelgeuse stands out not just as a bright star, but as an example of what happens when a massive star reaches this stage. It is not alone in the universe, but it is close enough and large enough for us to study in detail. If this is what a supergiant star is, if this is how it expands and changes, then what does that expansion actually look like in terms we can grasp more directly? How far does it reach? How does its size compare to the space we know so well? Now that the idea of Betelgeuse as a fully developed red supergiant has settled into place, with its layered interior and vast shifting surface, it becomes easier to focus on the part that tends to stretch the imagination the most. Not just that it is large, but how that size actually unfolds in space. What does it mean, in practical terms, for a star to expand so dramatically that its outer layers reach distances we usually associate with entire planetary systems? It helps to start slowly, without jumping straight into numbers. Imagine the Sun again, sitting quietly at the centre of our solar system. Its size, though enormous compared to Earth, still feels manageable when you think about the scale of the planets. Mercury orbits relatively close, then Venus, then Earth at a comfortable distance, and beyond that Mars, Jupiter, and the outer world stretching farther into space. Now, gently replace the Sun with Betelgeuse. At first the change might not feel immediate. The centre is still there, the reference point unchanged. But then the star begins to expand, not explosively, not all at once, but steadily, pushing outward, layer by layer. Its surface grows larger, extending beyond what used to be the orbit of Mercury. That alone is already a staggering increase, but it doesn't stop there. The expansion continues. Venus's orbit, once safely distant from the Sun, now lies well within the star's outer layers. Earth follows, its familiar path swallowed by the growing sphere. The orbit that defines our year, the distance that feels so fundamental to our sense of place, becomes just another point inside the star. And still, the expansion continues. Mars, often thought of as a distant neighbour, is drawn into this vast envelope. In many estimates, Betelgeuse's outer layers would stretch beyond Mars, reaching into regions we associate with the asteroid belt. Some measurements suggest it could extend even farther, approaching or overlapping with the orbit of Jupiter, depending on how one defines the star's edge. That last detail is worth pausing on for a moment, because it reveals something important. Betelgeuse does not have a sharp boundary. Unlike a planet which has a clear surface, or even the Sun, which has a more defined photosphere, Betelgeuse's outer layers fade gradually into space. Its atmosphere is extended and diffuse, meaning that the exact point where the star ends depends on how you measure it. Some wavelengths of light come from deeper layers, others from higher, more tenuous regions. So when we say that Betelgeuse might reach as far as Jupiter's orbit, we are describing a region where the star's material is still present, still part of its structure, even if it is thin and spread out. This makes the concept of size a little more fluid. Instead of imagining a solid sphere, it helps to think of Betelgeuse as a vast, glowing volume, with denser regions toward the centre and increasingly diffuse material as you move outward. The star is not just large, it is expansive in a way that blurs the line between star and surrounding space. Another way to approach this is through volume. If you were to take the Sun and imagine filling Betelgeuse with suns, not just lining them up across its diameter, but packing them throughout its entire interior, you would need millions of them. The exact number depends on the measurements used, but the point remains the same. Betelgeuse's volume is so immense that even our largest familiar object, the Sun, becomes a small unit in comparison. And yet, despite this enormous size, Betelgeuse's mass is only about 15 to 20 times that of the Sun. This leads to an interesting consequence. Because its mass is spread out over such a large volume, the average density of Betelgeuse is extremely low. In fact, its outer layers are so diffuse that if you could somehow sample that material, it would feel closer to a vacuum than to anything we experience on Earth. The star is vast, but much of that vastness is made up of thin, tenuous gas. This combination of size and low density contributes to the star's behaviour. The outer layers are loosely bound by gravity, making them easier to push outward and easier to lose entirely. That's why Betelgeuse sheds material into space, forming a surrounding envelope of gas and dust. It's also why the star can expand and contract, its structure flexible in a way that smaller, denser stars are not. If you imagine standing at what we might call the surface of Betelgeuse, the experience would be very different from standing on a planet. There would be no solid ground, no clear boundary, just layers of gas gradually thinning as you move outward. The gravity, though still significant, would be much weaker than at the surface of a smaller star. The sense of being inside something enormous would come not from a solid edge, but from the vastness of the surrounding glow, the slow movement of material, the immense scale stretching in every direction. And that scale changes over time. Betelgeuse is not fixed at a single size. It pulsates. Over periods of months and years, the star expands slightly, then contracts, then expands again. These changes are driven by processes deep within the star, where energy production and pressure shifts ripple outward through its layers. The result is a gentle breathing motion, subtle but measurable, altering the star's radius by a noticeable amount. So when we talk about the Great Expansion, we're not referring to a single event but to an ongoing process. The star has already expanded enormously compared to its earlier state, and it continues to adjust its size in response to internal changes. Each cycle of expansion and contraction is part of a larger pattern, one that reflects the complex interplay of fusion, pressure, and gravity within the star. There's also an interesting perspective shift that happens when you think about this expansion in terms of distance rather than size. Instead of asking how big Betelgeuse is, you might ask how far its influence extends. Its light, for instance, travels across hundreds of light years to reach Earth. Its stellar wind, the flow of particles streaming away from the star, carries material outward into the surrounding space. Over time, that material mixes with the interstellar medium, contributing to the formation of future stars and planets. In this sense, the star's reach goes beyond its physical size. It extends into the space around it, shaping its environment, leaving traces that persist long after the star itself has changed. The expansion we see now is part of a larger cycle, one where matter is redistributed, where elements forged in the star's core are eventually released into the galaxy. Returning to the visual experience though, it's worth grounding this again in something simple. When you look up and see Betelgeuse, none of this expansion is obvious. There's no visible disk, no sense of scale in the way we perceive nearby objects. The star remains a point of light, its true size hidden behind distance. And yet, knowing what lies behind that point changes how you see it. It's no longer just a star among many. It becomes a vast, expanding giant, occupying a volume that could swallow the inner solar system, its outer layers stretching across distances we usually reserve for planets and orbits. There's a quiet shift in perception that comes with that knowledge. The sky doesn't look different, but it feels different. The points of light take on depth, scale, history. Betelgeuse in particular becomes something more than a marker in Orion. It becomes a presence, a reminder of how large and varied stars can be. And as that sense of scale settles in, it naturally leads to another layer of curiosity. If Betelgeuse is this large, if its outer layers extend so far, then what is happening at its surface? What does that vast diffuse boundary actually look like in terms of temperature, colour and structure? That soft red-orange glow that first catches your eye when you look toward Orion is not just a visual detail, it's a direct clue, a quiet piece of information about what is happening on the star's surface, or more precisely, in the outer layers where its light is released into space. If you've ever compared stars in the night sky, you might have noticed that not all of them look the same. Some appear bluish, some white, some slightly yellow, and a few, like Betelgeuse, carry that warm reddish tone. These colours are not random, and they're not tricks of the atmosphere, at least not entirely. They are tied closely to temperature, and understanding that relationship gives us a way to read a star, almost as if its colour were a kind of language. To begin, it helps to think about heat and light in a familiar context. Imagine heating a piece of metal. At first it might appear dark, then as it warms it begins to glow faintly red. Increase the temperature further and the colour shifts toward orange, then yellow, and eventually at very high temperatures it can appear white or even bluish. This progression is something we can observe directly, and it reflects how objects emit light at different temperatures. Stars follow the same basic principle. Betelgeuse, with its red-orange glow, is cooler at its surface than stars that appear white or blue. Its surface temperature is roughly 3,500 degrees Celsius, which is still unimaginably hot by everyday standards, but significantly cooler than the Sun's surface, which sits around 5,500 degrees Celsius. Hotter stars, those glowing blue-white, can reach temperatures of 10,000 degrees Celsius or more. So when you see Betelgeuse shining with that warm hue, you are, in a sense, seeing its temperature. It's a subtle but powerful connection. Light carries information, and your eyes, without realizing it, are detecting differences in that light that correspond to physical properties of a distant object. No instruments required, just careful observation and a bit of understanding. But with Betelgeuse, colour is not entirely uniform. Because of its immense size and dynamic surface, different regions of the star can have slightly different temperatures. The enormous convection cells we mentioned earlier bring hotter material up from the interior and allow cooler material to sink back down. This creates patches across the surface that are brighter or dimmer, slightly hotter or slightly cooler. From Earth, these variations blend together, giving the star its overall reddish appearance. But with advanced imaging techniques, astronomers have been able to detect these irregularities, revealing that the surface is not smooth or consistent, it's mottled, shifting, constantly in motion. This means that when we talk about the temperature of Betelgeuse, we're really talking about an average. There isn't a single, fixed temperature across the entire surface. Instead, there is a range, with different regions contributing to the light we see. Some areas may be slightly hotter, glowing a bit brighter, while others are cooler and dimmer. Over time, these regions change, adding to the star's variability. Another layer to this is the star's atmosphere. Betelgeuse does not have a sharp surface like a planet. Instead, it has an extended atmosphere that stretches outward, gradually thinning as it reaches into space. The light we see comes from different depths within this atmosphere, depending on the wavelength we observe. In visible light, we are seeing the region where the star becomes opaque, where photons can finally escape into space. But above that, there are layers of gas that continue outward, influencing how the light is scattered and absorbed. This can subtly affect the colour and brightness we perceive. In some cases, dust forms in these outer layers. When Betelgeuse ejects material, that gas can cool and condense into tiny dust particles. These particles interact with light, absorbing some wavelengths and scattering others. This process can make the star appear dimmer or slightly alter its colour, especially during events like the Great Dimming. So the colour we see is not just a simple reflection of temperature. It is shaped by multiple factors: the star's surface conditions, its atmospheric layers, and the material surrounding it. Even the journey of the light itself plays a role. As the light travels across hundreds of light years, it passes through interstellar space, encountering gas and dust that can slightly redden it, a process known as interstellar extinction. This effect is usually small, but it adds another subtle layer to how we perceive the star. Despite all these complexities, the overall impression remains clear and consistent. Betelgeuse is a red supergiant, and its colour reflects that identity. It tells us that the star is in a late stage of its life, that its surface has cooled as it expanded, and that it is no longer the hot blue-white star it once was. There's something quietly intuitive about this. As Betelgeuse grew larger, it also grew cooler at the surface. The energy it produces is spread over a much larger area, reducing the intensity at any given point. The shift from blue-white to red-orange is a natural consequence of that change, a visual signature of the star's evolution. If you compare Betelgeuse to other stars in Orion, this becomes even more apparent. Rigel, for example, shines with a blue-white light, indicating a much higher surface temperature. The contrast between the two stars is subtle but noticeable, especially in a dark sky. One appears cooler and more diffuse, the other hotter and sharper. This contrast is a reminder that stars, even within the same constellation, can be vastly different. They may appear close together from our perspective, but in reality, they can be separated by hundreds or even thousands of light years, each following its own path through the stages of stellar evolution. Returning to Betelgeuse, its colour also changes slightly over time. As the star pulsates, expanding and contracting, its surface temperature can shift a little, leading to small variations in its hue and brightness. These changes are not dramatic to the naked eye, but they are measurable, and they provide insight into the processes occurring within the star. It's a bit like watching a slow, steady rhythm. The star brightens, dims, shifts slightly, all over timescales that encourage patience rather than urgency. Observing these changes requires returning to the sky again and again, allowing patterns to emerge gradually. And there's something fitting about that. A star of this size, this age, and this complexity does not reveal itself all at once. It invites slow observation, quiet attention, a willingness to notice small differences over long periods of time. Even the idea of reading the star's skin carries a gentle sense of interpretation. We're not touching it, not interacting with it directly. Instead, we're interpreting the light it sends us, decoding information carried across vast distances. The colour becomes a clue, the brightness a hint, the variability a signal, all of it combining into a picture that we assemble piece by piece. In this way, Betelgeuse becomes more than just an object in the sky. It becomes a source of information, a messenger of physical processes happening far beyond our reach. Its colour tells us about temperature, its brightness tells us about size and energy output. Its changes tell us about internal dynamics and surface activity, and yet All of this is delivered through something as simple as light. There's a quiet elegance in that. A star can communicate so much, not through sound or motion we can directly perceive, but through the steady emission of photons, each one carrying a tiny piece of the story. When those photons reach us, they combine into the glow we see, and with a bit of understanding, that glow becomes meaningful. As you picture Betelgeuse now, not just as a large star, but as a warm, glowing sphere with a shifting surface and an extended atmosphere, its colour takes on a new significance. It is no longer just a visual detail. It is a sign of its stage in life, a reflection of its internal processes, a clue to its structure and behaviour. It connects the idea of size to something more tangible, something you can actually see and recognise. As that warm reddish glow begins to feel more meaningful, no longer just a colour but a sign of temperature and structure, it becomes easier to imagine that the surface of Betelgeuse is not calm or uniform at all. What looks steady from Earth is, in reality, a place of constant motion, shaped by forces that move slowly but operate on scales that are almost difficult to accept at first. Instead of thinking of the surface as something smooth, it helps to imagine it as active, shifting, and uneven. Not violently chaotic in the way of an explosion, but restless in a slower, more persistent way. The key process behind this movement is something called convection, and while the term might sound technical, the basic idea is surprisingly familiar. You've likely seen convection in action without thinking about it. When water boils, you notice currents forming. Hot water rises from the bottom, cools slightly near the surface, and then sinks again. This creates a continuous cycle, a pattern of movement driven by differences in temperature and density. Now take that simple process and expand it beyond anything we experience on Earth. Inside Betelgeuse, energy generated deep in the core makes its way outward. In the outer layers, this energy is transported not just by radiation, but by convection. Hot gas rises toward the surface, cools as it releases energy into space, and then sinks back down to be reheated and lifted again. On the Sun, this process creates convection cells that are relatively small compared to the star itself. They form a kind of granular pattern across the surface, visible in detailed images as countless small regions of rising and falling gas. But Betelgeuse is not the Sun. Because it is so large and its gravity at the surface is much weaker, the convection cells on Betelgeuse are enormous. Instead of millions of small cells, there are only a handful of very large ones, each covering a significant portion of the star's surface. To get a sense of scale, a single convection cell on Betelgeuse can be comparable in size to the entire orbit of Earth around the Sun. That means these are not small ripples or minor disturbances. They are vast regions where material is moving slowly upward or downward, shaping the brightness and temperature across huge areas. Imagine standing far enough away to see the entire star at once. Instead of a uniform glow, you would notice brighter regions where hot gas is rising, and darker regions where cooler gas is descending. These patterns would shift over time, not quickly, but steadily, like slow-moving weather systems on a scale that makes even the largest storms on Earth seem insignificant. And this movement is not random. It follows the physics of heat transfer, gravity, and fluid dynamics, creating patterns that can persist for months or even years before changing. A bright region might dominate one part of the star, then gradually fade as the underlying convection cell evolves. Another region might grow in brightness, taking its place. From Earth, these changes are subtle. We cannot see the surface directly with our eyes, and even with most telescopes, Betelgeuse appears as a point of light. But with advanced imaging techniques, astronomers have been able to detect these large-scale features, confirming that the surface is indeed mottled and dynamic. This is one of the reasons Betelgeuse's brightness varies. As these giant convection cells shift, the overall amount of light we receive changes slightly. When more of the surface is dominated by hotter, brighter regions, the star appears brighter. When cooler regions become more prominent, it dims. This variability is not perfectly regular because the convection itself is not perfectly predictable. It is influenced by many factors, including the star's internal structure, its pulsations, and the interaction between different layers. Another interesting aspect of this turbulence is how it affects the star's atmosphere. As hot gas rises and reaches the outer layers, some of it can be pushed even farther outward, escaping the star's gravitational pull. This contributes to the mass loss we talked about earlier, where Betelgeuse sheds material into the surrounding space. These outflows are not uniform either. They can be stronger in some regions than others, depending on where the most active convection cells are located. This creates an uneven distribution of gas and dust around the star, adding another layer of complexity to its appearance and behaviour. If you imagine this process over time, you start to see Betelgeuse not as a static sphere, but as something more like a slow living system. Its surface rises and falls, its brightness shifts, its outer layers expand and drift away. All of this happening continuously, quietly, without any sudden or dramatic changes that we can easily perceive from Earth. There is also a connection between these convection cells and the star's pulsations. As Betelgeuse expands and contracts slightly, the conditions within its outer layers change. This can influence how convection operates, altering the size, strength, and behaviour of the cells. In turn, the convection can affect how energy is transported, feeding back into the pulsation cycle. It's a complex interaction, one where multiple processes are linked together, each influencing the others in subtle ways. Even the temperature variations we discussed earlier are tied to this. The rising gas in a convection cell is hotter and therefore brighter, while the sinking gas is cooler and dimmer. This creates a patchwork of temperatures across the surface, which contributes to the overall colour and brightness of the star. From a distance, all of these variations blend together into that familiar red-orange glow. But knowing what lies beneath that glow changes how you think about it. It's no longer just a steady light. It becomes a surface in motion, a vast shifting landscape of gas and energy, shaped by forces that operate on scales far beyond anything we encounter in daily life. There's also something quietly fascinating about the speed of these processes. On Earth, we're used to changes happening quickly. Weather systems move across continents in days. Boiling water changes in seconds. Even the sun's surface, though dynamic, evolves on relatively short timescales. Betelgeuse moves more slowly. A convection cell can take months or years to fully develop and change. The star's pulsations unfold over long periods. The shifts in brightness are gradual, encouraging patience rather than immediate observation. This slower pace gives the star a kind of calm presence, even though the processes themselves are immense and powerful. If you were somehow able to observe Betelgeuse up close over an extended period, you might see its surface changing in a way that feels almost geological, like continents of glowing gas slowly rearranging themselves, rather than storms raging or explosions occurring. And yet, despite this slow pace, the energy involved is enormous. Each convection cell carries vast amounts of heat from the interior to the surface. The rising and falling gas represents a continuous flow of energy, part of the star's effort to maintain balance between the forces within it. This balance, as we've seen, is delicate. As Betelgeuse continues to evolve, these processes will change. The convection patterns may become more or less pronounced. The pulsations may shift. The mass loss may increase or decrease. All of this is part of the ongoing story of a star nearing the end of its life. But for now, what we observe is a star with a surface that is anything but still. It is a place of slow turbulence, of giant convection cells rising and falling, of brightness and temperature shifting across immense distances. It is a reminder that even something that appears calm from afar can be filled with motion and change when viewed more closely. As you hold that image in your mind, the idea of Betelgeuse becomes richer, Not just a large star, not just a red supergiant, but a dynamic system with a surface that moves and evolves in ways that are both subtle and profound. And as that understanding settles, it naturally leads to another question. If the surface is constantly shifting, if convection and pulsation are influencing the star's brightness, then how do these changes appear over time? What patterns can we observe, and what do they tell us about the deeper processes at work within Betelgeuse? As that image of a shifting, uneven surface settles into place, with those enormous convection cells slowly rising and falling, it becomes easier to notice that Betelgeuse is not just changing locally across its surface, but also globally as an entire star. There is a kind of rhythm to it, not perfectly regular, not like the ticking of a clock, but present nonetheless. A gentle expansion, a slight contraction, a subtle brightening, then a dimming. These are the pulsations of Betelgeuse, and they form one of the most important clues to understanding how this giant behaves over time. It helps to begin with a simple idea. A star, especially one as large as Betelgeuse, is not a rigid object. It is made of gas, held together by gravity, with pressure pushing outward from the energy produced inside. Because of this, the star can expand and contract, almost like a slow, steady breathing motion. Not in the sense of air moving in and out, but in the way its outer layers shift position, moving outward and inward over time. For Betelgeuse, these changes are measurable. Astronomers have observed that its brightness varies over periods of several hundred days, with additional longer cycles layered on top. One commonly noted period is around 400 days, during which the star gradually brightens and dims. There are also longer-term variations that can stretch over several years, creating a more complex pattern when you look at the data over extended time. This variability is what places Betelgeuse in the category of semi-regular variable stars. The term semi-regular is important here. It means that while there are patterns, they are not perfectly predictable. The star does not follow a strict repeating cycle like a metronome. Instead, it shows tendencies, rhythms that can shift slightly, periods that can lengthen or shorten, amplitudes that can grow or shrink. If you were to track its brightness night after night, plotting it on a graph, you would see a series of gentle waves, rising and falling, but not in identical shapes. Some peaks would be higher, some lower. Some dips would be deeper, others more shallow. Over time, the pattern would feel familiar but never exactly the same. What drives these pulsations? At the core, it comes down to the balance between gravity and pressure. When the outer layers of the star expand, they cool slightly. As they cool, the pressure that was pushing outward decreases, allowing gravity to pull those layers back inward. As the layers contract, they heat up again, increasing the pressure and pushing outward once more. This cycle can repeat, creating a natural oscillation. In Betelgeuse, this process is influenced by several additional factors. The layered fusion inside the star means that energy production is not confined to a single stable region. Different shells contribute energy at different rates, and this can affect how pressure builds and dissipates. The convection cells we discussed earlier also play a role, redistributing energy unevenly across the star's surface. All of these processes interact, creating a system where pulsations are present but not perfectly uniform. There's also an interesting connection between the star's size and the timescale of its pulsations. Because Betelgeuse is so large, it takes longer for changes to propagate through its structure. A disturbance in one part of the star does not instantly affect the entire system. Instead, it moves outward over time, influencing the outer layers gradually. This contributes to the relatively long periods we observe, on the order of months to years rather than minutes or hours. Another aspect to consider is how these pulsations affect the star's brightness. When Betelgeuse expands, its surface area increases. At the same time, its surface temperature decreases slightly. These two effects compete with each other. A larger surface area tends to increase brightness, while a cooler temperature tends to decrease it. The net result depends on which effect dominates at a given time. When the star contracts, the opposite happens. The surface area decreases, but the temperature rises. Again, the balance between these factors determines how the brightness changes. This interplay is part of why the variability is not perfectly regular. It's not just a simple expansion leading to dimming or contraction leading to brightening. Multiple factors are at work, and their combined effect creates the patterns we observe. Now, from Earth, these changes are subtle. To the casual observer, Betelgeuse may appear steady night after night. But if you compare it carefully to nearby stars, especially over longer periods, you can begin to notice differences. At times, it can appear almost as bright as the other prominent stars in Orion. At other times, it seems noticeably dimmer. For those who enjoy observing the night sky regularly, this becomes a quiet exercise in attention. You look up, find Orion, locate Betelgeuse, and compare it to its neighbours. Over weeks and months, you begin to sense the changes, not as dramatic events, but as gentle shifts. It's a kind of slow observation that rewards patience, allowing you to connect with the star's rhythm in a very direct way. And then there are moments when the variability becomes more pronounced. The most famous recent example is the great dimming that occurred between late 2019 and early 2020. During this period, Betelgeuse's brightness dropped significantly, far more than its usual variations. It became noticeably fainter, enough that even casual observers could see the difference. This event sparked widespread interest and speculation. Some wondered if it was a sign that the star was about to explode as a supernova. Others suggested more immediate explanations such as surface changes or the formation of dust clouds. As it turned out, the dimming was likely caused by a combination of factors. A large convection cell brought cooler material to the surface, reducing the star's temperature in that region. At the same time, Betelgeuse ejected a significant amount of material, which cooled and formed dust. This dust cloud then partially obscured the star's light from our point of view. The result was a noticeable drop in brightness, not because the star itself had dramatically changed its energy output, but because of changes in its surface and surroundings. This event highlights an important point. Variability in Betelgeuse is not driven by a single process. It is the result of multiple interacting factors, including pulsations, convection, and mass loss. Each of these can influence the star's brightness, sometimes reinforcing each other, sometimes working in different directions. From a scientific perspective, studying these variations provides valuable information. By analysing the timing, amplitude, and patterns of the pulsations, astronomers can infer details about the star's internal structure. It's a bit like listening to the vibrations of a musical instrument to understand its shape and material. The way Betelgeuse rings with these pulsations tells us something about what's happening inside. There's also a broader significance. Stars like Betelgeuse are not unique in their variability. Many red giants and supergiants show similar behaviour, though each has its own patterns and characteristics. By studying Betelgeuse in detail, astronomers can refine models that apply to other stars as well, improving our understanding of stellar evolution more generally. At the same time, there's something quietly personal about observing these changes. Unlike distant galaxies or abstract measurements, Betelgeuse's variability can be followed with the naked eye. It's one of the few stars where you can, over time, notice real changes without needing advanced equipment. That creates a connection between observer and object, a sense that you are not just learning about the star, but witnessing its behaviour directly. And yet, even with this direct observation, there is always a layer of distance. The changes you see tonight are not happening now in the star's frame of reference. They happened centuries ago, and the light has only just arrived. So in a sense, you are watching a delayed performance, a record of past events unfolding in your present. This adds a quiet depth to the experience. The pulsations you observe are both immediate and historical. part of a timeline that stretches far beyond a single human life. It reminds you that the universe operates on scales of time that are different from our own, where even slow changes can span decades or centuries. As you hold that idea, the variability of Betelgeuse begins to feel less like a technical detail and more like a characteristic, something that defines how the star exists. It is not static. It does not remain the same from one moment to the next. It shifts, breathes, adjusts, following patterns that are partly predictable and partly complex. And as those patterns continue, they influence not just the star's brightness, but also its structure, its atmosphere, and the material it releases into space. So the gentle rise and fall of its light, the subtle changes you might notice over time, are part of a larger story. One that connects the surface to the interior, the present to the past, and the quiet act of observation to the immense processes unfolding within a star that continues to evolve, cycle after cycle, carrying its rhythm forward. We've talked about how big it is, how it changes, how it moves internally, but all of that depends on something even more fundamental. How far away is it? Because without distance, size has no meaning. A small object nearby can look large, and a truly enormous object far away can appear tiny. Betelgeuse, as we see it, is just a point of light. Everything we've discussed so far, its massive radius, its expansion, its surface motion, all of that depends on knowing how far that light has travelled to reach us. So how do we measure that? It's not as though we can stretch a measuring tape across space. We can't send a probe there and back within any reasonable time frame. Instead, astronomers rely on indirect methods, each one carefully built on observation, geometry, and a bit of patience. The most direct method for relatively nearby stars is something called parallax. The idea is simple, even if the execution is delicate. As Earth orbits the Sun, our viewpoint changes slightly. When we observe a nearby star at one point in Earth's orbit, and then again 6 months later from the opposite side, that star appears to shift slightly against the background of more distant stars. It's a very small shift. To picture it, you can hold your thumb up at arm's length and look at it with one eye, then switch to the other. Your thumb seems to jump slightly relative to the background. The closer your thumb is, the larger the shift. Stars behave the same way, but because they are so far away, the shift is incredibly tiny. For Betelgeuse, this shift is measured in fractions of an arcsecond, which, as we mentioned earlier, is already a very small unit. Detecting such a minute change requires extremely precise instruments. Historically, this was difficult. Early astronomers suspected parallax should exist, but they couldn't detect it with the tools available at the time. It wasn't until the 19th century that parallax measurements were successfully made for nearby stars. Even then, the accuracy was limited. With modern technology, however, things have improved dramatically. Space-based observatories like Hipparcos and later Gaia have been able to measure stellar positions with extraordinary precision. By tracking tiny shifts over time, they can calculate distances to stars across large portions of our galaxy. Using these methods, Betelgeuse is estimated to be roughly between 500 and 700 light-years away from Earth. That range might seem broad, but given the challenges involved, it's actually quite precise. And this is where things become especially interesting. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. So when we say Betelgeuse is around 600 light-years away, we're saying that the light we see tonight left the star around the time of the late Middle Ages on Earth. Think about that for a moment. While that light was beginning its journey, entire civilizations have risen and fallen, languages have changed, technologies have advanced, and generations have come and gone. And only now is that light arriving, carrying information about the state of Betelgeuse centuries ago. So when you look at the star, you're not seeing it as it is now, but as it was hundreds of years in the past. That idea can feel a little unusual at first, but it's a natural consequence of distance. The farther away something is, the longer its light takes to reach us, and the further back in time we're effectively looking. Now, measuring Betelgeuse's distance is not as straightforward as measuring a smaller, more stable star. One of the complications is that Betelgeuse is large and irregular. Its surface is not a perfect sphere, and its brightness can shift due to convection, pulsation, and dust. This makes it harder to define a precise center point for measurement, which introduces some uncertainty into parallax calculations. There are also additional methods that help refine distance estimates. Astronomers can use something called spectroscopic parallax, which involves analyzing the star's spectrum to determine its intrinsic brightness, then comparing that to how bright it appears from Earth. The difference gives an estimate of distance. They can also look at Betelgeuse's motion through space, its association with nearby stars, and its place within the Orion region to cross-check measurements. Even with all these methods, there is still a margin of uncertainty. But what matters most is that we have a reliable sense of the scale involved. Betelgeuse is not just far away, it is hundreds of light years distant, placing it within our galaxy, but still far beyond the reach of any current or near-future human travel. And yet, despite that distance, its light is bright enough to be seen easily with the naked eye. This tells us something important. For a star to be visible from so far away, it must be extremely luminous. Betelgeuse emits vast amounts of energy, far more than the Sun. Its brightness, combined with its size, makes it one of the most prominent stars in our sky. There's also a subtle connection between distance and how we perceive variability. Because Betelgeuse is so far away, the changes we observe in its brightness are smoothed out by distance and time. The light we receive is an average over the entire visible surface, and the time it takes to reach us means we're always seeing a slightly delayed version of events. If we were closer, the variations might appear more pronounced, more immediate. But from Earth, they unfold slowly, blending into the gentle rhythm we discussed earlier. Another way to think about distance is in terms of scale within our galaxy. The Milky Way is about 100,000 light-years across, so at around 600 light-years away, Betelgeuse is relatively close on a galactic scale. It's part of our local neighbourhood, so to speak, even though that neighbourhood is vast compared to anything we experience directly. This relative closeness is what allows us to study it in such detail. More distant red supergiants exist, some even larger, but they are too far away for us to resolve their surfaces or track their variability as precisely. Betelgeuse, by contrast, is close enough to serve as a kind of laboratory, a place where we can observe these processes more directly. And yet, even at this close distance, the scale remains immense. If you could travel at the speed of the fastest spacecraft we've ever built, it would still take tens of thousands of years to reach Betelgeuse. Even at a significant fraction of the speed of light, the journey would span generations. So while we can measure the distance and understand it mathematically, experiencing it directly is another matter entirely. There's something quietly humbling about that. We can know where Betelgeuse is, how far away it lies, how large it must be, and yet it remains beyond our physical reach. Our connection to it is through light, through observation, through the interpretation of data carried across space. And that connection is enough. Because through it, we can build a picture of the star, not just as a distant object, but as something with structure, motion, and history. As this idea of distance settles in, it also begins to reshape how we think about size again. Knowing that Betelgeuse is hundreds of light years away, and still appears bright and distinct in our sky, reinforces just how enormous and luminous it must be. The farther something is, the more energy it must emit to remain visible. So distance and size are intertwined. The measurements we discussed earlier, the calculations of radius and volume, all depend on this understanding of how far the star is from us. Without distance, those numbers would lose their meaning. Picture, for a moment, the familiar layout of our solar system as you know it. The Sun sits calmly at the centre, its light reaching outward, illuminating the orbits of Mercury, Venus, Earth, and the rest. The distances between these planets feel vast when we think about them in everyday terms. Millions of kilometres separate each orbit, And yet, compared to what we've been discussing, this entire system begins to feel almost compact. Now, instead of thinking about Betelgeuse as something distant, place it gently into that same space. Not in the sky, not hundreds of light years away, but right here, where the sun currently resides. At first, the change is subtle in your imagination. The position is the same, the centre remains the centre, but the scale begins to shift almost immediately. Betelgeuse does not sit quietly within the orbit of Mercury. It doesn't even stop at Venus. Its outer layers extend far beyond what we usually consider the inner solar system. Mercury disappears first, its orbit completely engulfed. Venus follows, then Earth, then Mars. All of these familiar paths, the distances that define our sense of space, are now well within the star's enormous volume. Pause there for a moment. The distance from Earth to the Sun, about 150 million kilometers, feels significant in everyday terms. It defines our year, our seasons, the rhythm of life on this planet. And yet within Betelgeuse, that entire distance would not even reach the surface. It would sit somewhere inside, surrounded by layers of glowing gas. If you imagine standing at the location where Earth's orbit used to be, you wouldn't be looking at a distant star anymore. You would be inside it. There would be no clear boundary marking where the star begins. Instead, you would be immersed in its outer atmosphere, surrounded by a vast diffuse glow. The concept of surface becomes less meaningful here, because Betelgeuse does not have a solid edge. Its outer layers fade gradually, becoming thinner as they extend outward, and the expansion does not necessarily stop at Mars. Depending on how one defines the star's radius, especially when including its extended atmosphere, Betelgeuse could reach into the region of the asteroid belt, and in some models even approach the orbit of Jupiter. That's a distance of hundreds of millions of kilometers from the centre. To place that in context, Jupiter orbits the Sun at about 5 times the distance between Earth and the Sun. Imagining a single star filling that space begins to stretch the mind in a different way. But there's an important detail here that softens the image slightly. Betelgeuse is not dense like a planet or even like the Sun. Its outer layers are extremely diffuse. The material is spread out, thin, more like a very sparse gas than anything solid. So while the star occupies that space, it does not fill it with the same intensity throughout. The deeper you go toward the centre, the denser and hotter it becomes. The outer regions are more like a glowing mist, still part of the star but far less concentrated. This means that if Earth somehow found itself inside Betelgeuse's outer layers, it wouldn't encounter a sudden solid barrier. Instead, it would move through increasingly dense and hot gas, with conditions changing gradually rather than abruptly. Still, those conditions would not be survivable. Even though the outer layers are cooler compared to the core, they are still thousands of degrees hot, filled with radiation and moving plasma. The idea of standing there is purely conceptual. It's a way to visualize scale, not a scenario that could exist in reality. Now consider how this would affect the rest of the solar system. The inner planets would no longer orbit freely in empty space. They would be embedded within the star itself. Their orbits, if they could even persist, would be entirely different, influenced by the drag of stellar material and the altered gravitational environment. Beyond that, the outer planets would still remain outside the main body of the star, at least in most estimates. Jupiter, Saturn, Uranus and Neptune would orbit beyond the densest regions, though they would be much closer to the star's extended atmosphere than they are to the Sun's. The sky, from those planets, would look very different. Instead of a relatively small sun, they would see a vast, swollen star dominating the view, its surface extending across a large portion of the sky. The light would be redder, softer in colour, but still incredibly bright. The sense of scale would be overwhelming, with the star appearing not as a distant object, but as a massive presence filling much of the visible space. There's also an interesting shift in how we think about distance when imagining this scenario. In our current solar system, distances between planets are measured in millions or billions of kilometers, and those distances feel significant. But when the central star itself spans such a large region, those same distances begin to feel compressed in comparison. The orbit of Earth, which defines our sense of space, becomes just a small fraction of the star's size. The gap between Earth and Mars, something we consider vast, becomes a minor detail within the star's interior. This change in perspective is one of the most useful aspects of this thought experiment. It takes the abstract idea of Betelgeuse's size and places it into a framework we understand. Instead of thinking in terms of hundreds of times the Sun's radius, we can think in terms of orbits, distances we already know, and how they would be affected. Another layer to consider is how Betelgeuse's variability would play out in this scenario. Because the star expands and contracts slightly over time, its outer layers would shift relative to these orbital distances. During one phase, it might extend farther, reaching deeper into the solar system. During another, it might contract slightly, pulling its outer boundary inward. These changes would not be dramatic on a human timescale, but over months and years they would be noticeable. Imagine watching the edge of the star slowly move, not as a sharp line, but as a gradual change in density and brightness. The environment would feel dynamic, with the boundaries of the star subtly shifting over time. There's also the matter of luminosity. Betelgeuse is far more luminous than the Sun, even though its surface is cooler. Because it is so large, it emits an enormous amount of energy overall. If it replaced the Sun, the amount of radiation reaching the outer planets would increase significantly, altering temperatures and conditions throughout the system. Even at distances where planets remain outside the star's main body, the increased luminosity would change their environments in profound ways. At the same time, the redder light of Betelgeuse would give everything a different appearance. Instead of the bright white-yellow sunlight we're used to, the illumination would be softer, more orange-red. Shadows would look different. Colours would shift. The entire visual character of the solar system would change, shaped by the star's temperature and spectral output. Returning to the central idea, though, what stands out most is the sheer scale. Replacing the Sun with Betelgeuse transforms the solar system from a wide, open space into something that feels almost contained within the star itself. The distances that once defined our sense of separation become part of a single, continuous structure. And yet, even this comparison has its limits, because while placing Betelgeuse in our solar system helps us visualize its size, it is still only an approximation. The star's true nature, with its diffuse atmosphere, its shifting surface, and its ongoing expansion and contraction, is more complex than any simple model can capture. Still, the exercise serves its purpose. It gives us a way to connect something distant and abstract to something familiar. It allows us to take the idea of a red supergiant and anchor it in a space we understand, even if only temporarily. And as that image settles in, with Betelgeuse filling the inner solar system, its outer layers stretching across planetary orbits, it becomes easier to appreciate not just how large it is, but how different it is from the Sun and other stars we encounter more directly. From here, another question begins to form naturally. If Betelgeuse can grow this large, if its structure can extend so far while remaining relatively diffuse, then what holds it together? How does gravity balance against all that expansion? What keeps such a massive, spread-out star from simply dispersing into space? At first glance, size might suggest strength. We often associate larger things with greater stability, with more resistance to change. A mountain feels immovable, an ocean feels endless, and something the size of Betelgeuse might seem almost invincible. But in the case of stars, especially ones like this, size and stability don't always go hand in hand. Betelgeuse is massive, yes, somewhere between 15 and 20 times the mass of the Sun. That's a tremendous amount of material, all gathered into a single structure. But that mass is spread out across an enormous volume, far larger than anything we encounter in our solar system. The result is something that feels almost paradoxical. A star that is both immense and, in a certain sense, delicate. To understand this, it helps to return to the basic forces at work inside any star. Gravity is always pulling inward. Every particle of gas within Betelgeuse is attracted to every other particle, all of it trying to collapse toward the centre. This inward pull is what gives the star its shape, holding it together against the tendency of its material to spread out into space. At the same time, there is pressure pushing outward. This pressure comes from the energy produced by nuclear fusion deep within the star. As lighter elements fuse into heavier ones, energy is released, heating the surrounding material and creating outward pressure. This pressure works against gravity, preventing the star from collapsing. In a stable star, these two forces are in balance. But in Betelgeuse, that balance is not as steady as it is in a smaller main sequence star like the Sun. The internal structure is more complex, with multiple layers of fusion, shifting convection currents, and an extended outer atmosphere that is only loosely bound. Because the star is so large, the gravitational pull at its surface is relatively weak compared to the Sun. This is a key point. Even though Betelgeuse has much more mass overall, that mass is spread across such a large radius that the surface gravity is actually lower. If you could somehow stand in its outer layers, the pull inward would feel much gentler than the gravity at the surface of the Sun. This weaker gravity makes the outer layers easier to disturb. The gas in those regions does not need a great deal of energy to move outward. Convection currents can lift material, pulsations can push it farther, and in some cases that material can escape entirely, drifting away into space. This is why Betelgeuse is constantly losing mass. It is shedding its outer layers, releasing gas and dust into the surrounding environment. Over time, this material forms a kind of envelope around the star, a diffuse cloud that carries away some of its substance. So while the star remains intact, it is not perfectly contained. It is gradually giving itself away. There's something quietly interesting about that. A star that appears so dominant in the sky is in fact slowly dispersing, its material spreading outward, contributing to the broader structure of the galaxy. Another factor that contributes to this sense of fragility is the internal layering of the star. As Betelgeuse evolves, it builds up different shells of fusion, each one producing energy in its own way. Hydrogen may still be fusing in an outer shell, helium deeper inside, and heavier elements forming closer to the core. These layers do not always interact smoothly. Changes in one layer can affect the others, altering the flow of energy and the balance of pressure. This can lead to instabilities, small shifts that ripple outward through the star, contributing to its pulsations and variability. In a smaller star, these processes are more contained. In Betelgeuse, they are amplified by its size. The sheer scale of the star means that even small changes in internal conditions can have large effects on its outer layers. A slight increase in energy output in one region can push material outward over vast distances. A shift in convection patterns can change the distribution of heat across the surface. All of this adds to the impression that Betelgeuse is not a rigid structure, but a dynamic one. It is constantly adjusting, responding to internal and external influences, maintaining its overall shape while allowing for significant local variations. There's also the matter of time scale. The processes that govern Betelgeuse's behaviour unfold over long periods, but not as long as the earlier stages of its life. As a massive star nearing the end of its evolution, it is moving through its remaining phases more quickly. This doesn't mean sudden changes on a human timescale, but it does mean that the star is less stable than it once was. Its internal balance is more delicate, its outer layers more easily disturbed, its structure more prone to variation, and yet, despite all of this, Betelgeuse continues to exist as a coherent object. Gravity still holds it together. Fusion still provides the energy needed to resist collapse. The star has not yet reached the point where its internal processes can no longer sustain that balance. That point will come eventually. As heavier elements build up in the core, the ability to generate energy through fusion will decrease. When iron forms in significant quantities, fusion will no longer provide the outward pressure needed to counteract gravity. At that moment, the balance will fail. But that is not where Betelgeuse is right now. For the time being, it remains in a state of managed instability, if you can call it that. A star that is both stable enough to hold together and unstable enough to show variability, mass loss, and structural changes. There's a certain elegance in that balance. It is not a perfect equilibrium, but a dynamic one, constantly shifting, always adjusting, never entirely at rest. If you think back to the earlier image of Betelgeuse filling the solar system, this adds another layer of understanding. That vast volume is not a solid, unchanging mass. It is a region where forces are in motion, where gravity and pressure are in continuous dialogue, where material can move, shift, and even escape. The star's enormity does not make it unbreakable. In fact, in some ways, it makes it more vulnerable. Its outer layers are easier to lose, its internal processes are more complex, its future is closer in a cosmic sense than that of a smaller, more stable star. And yet, from our perspective, it remains a steady presence in the sky. Night after night it rises and sets, its reddish glow unchanged to the casual observer. The fragility we're describing is not something we see directly. It is something we infer, something we understand through observation and theory. This contrast is part of what makes Betelgeuse so compelling. It appears calm, but it is active. It appears stable, but it is evolving. It appears permanent, but it is in fact temporary. Holding that idea gently without rushing past it allows the star to feel a little more real, not just as a distant object, but as something with a structure, a balance, a set of forces that keep it together even as it changes. And as that understanding settles, another question begins to take shape. If Betelgeuse is both massive and fragile, held together by a balance that will not last forever, then what lies ahead? What does it mean for a star in this state to reach the end of its life, and how will that transition unfold when the balance finally gives way? The answer is both simple and deeply complex at the same time. Betelgeuse will eventually explode, not gently, not gradually, but in a sudden, powerful event known as a supernova. Yet before that moment arrives, there is a long and subtle preparation taking place inside the star, hidden from view, unfolding slowly over time. To understand this, it helps to return to the core. Deep inside Betelgeuse, beneath all the shifting layers and glowing atmosphere, nuclear fusion continues. Earlier the star burned hydrogen into helium, then helium into carbon and oxygen. As it aged, it moved on to fusing heavier and heavier elements, each stage producing energy for a shorter period than the last. This sequence continues inward, layer by layer. You can imagine it as a set of nested shells, the outer shells still processing lighter elements, the inner ones working on heavier ones. Each layer contributes energy, maintaining pressure that pushes outward against gravity. But there is a limit. Eventually the core begins to accumulate iron, and iron is different. Fusing lighter elements releases energy, which supports the star, but fusing iron does not release energy. Instead, it requires energy. That means once the core is dominated by iron, the star can no longer rely on fusion to maintain the balance between pressure and gravity. This is the turning point. Up until now, Betelgeuse has been able to hold itself together because the outward pressure from fusion counteracts the inward pull of gravity. But once iron takes over, that pressure begins to fade. Gravity, patient and constant, begins to win. The core collapses. This collapse happens incredibly quickly in a fraction of a second. The material in the core falls inward, compressing to extreme densities. Electrons are forced into protons, forming neutrons, and the core becomes something entirely new, a dense, compact object that resists further collapse. At the same time, the outer layers of the star are still moving inward. When they hit this suddenly rigid core, the motion reverses. A shock wave forms. That shock wave moves outward through the star, carrying enormous energy. It tears through the layers, accelerating material, heating it, and ultimately ejecting it into space. This is the supernova. For a brief time, Betelgeuse would become extraordinarily bright. Bright enough to be visible during the day, casting shadows at night, outshining nearly every other star in the sky. From Earth, it would appear as a brilliant point of light in Orion, far brighter than anything we're used to seeing there. And yet, despite how dramatic that sounds, it's important to pause and consider the timescale. When we say Betelgeuse is on the edge of exploding, we're speaking in a cosmic sense. It might happen in a few thousand years. It might take tens of thousands. It could even be longer. In astronomical terms, that's a short time. In human terms, it's far beyond any immediate concern. So there's no need to imagine it happening tonight or tomorrow. Instead, it's more accurate to think of Betelgeuse as being in the final chapter of a very long story. The ending is known, but the exact timing is not. And in the meantime, the star continues as it has been, pulsating, shedding material, shifting its surface, glowing steadily in the night sky. There's also something interesting about how we would experience such an event. Even though Betelgeuse is relatively close in astronomical terms, it is still hundreds of light years away. That distance provides a kind of safety. The explosion, while incredibly energetic, would not pose a danger to Earth. What it would provide is a rare opportunity, a chance to observe a supernova in detail, to study the process as it unfolds, to watch the formation of heavy elements and the transformation of a star in real time. Because supernovae are not just endings, they're also beginnings. The explosion disperses elements like carbon, oxygen, silicon, and iron into space. These elements become part of the interstellar medium, the raw material from which new stars and planets form. In a very real sense, events like the future explosion of Betelgeuse contribute to the ongoing cycle of creation in the galaxy. The atoms that make up planets, and even living things, are forged in stars and distributed by supernovae. So while the explosion marks the end of Betelgeuse as a red supergiant, it also ensures that its material continues on, becoming part of something new. There's a quiet continuity in that idea. Nothing is truly lost. It changes form, it moves, it becomes part of a larger process. Returning to the present though, Betelgeuse has not yet reached that final moment. Its core is still undergoing fusion, its layers are still structured in shells. The balance, while delicate, still holds. But the signs of its stage are there. The expansion, the variability, the mass loss. All of these point to a star that has moved beyond its stable youth and into a more dynamic, less predictable phase. Astronomers watch it closely for this reason, not because they expect an immediate explosion, but because Betelgeuse offers a rare opportunity to study a massive star near the end of its life. Each observation adds to our understanding, refining models, improving predictions, and revealing new details about how such stars evolve. And sometimes, as with the Great Dimming, it surprises us. Those moments remind us that even with all our knowledge, there is still complexity, still unpredictability, still room for discovery. From a human perspective, there's also something compelling about knowing that a star we can see with our own eyes is in this stage. It's not an abstract object in a distant galaxy, invisible without powerful instruments. It's right there in Orion, part of a familiar pattern, quietly carrying on while approaching an eventual transformation that will, one day, be visible across the sky. That connection between the everyday act of looking up and the immense processes unfolding within the star gives Betelgeuse a special place in our understanding of the cosmos. It becomes more than just a large star. It becomes a reminder of change, of cycles, of how even the most massive objects follow a path from formation to transformation. Look again at Orion, not just at Betelgeuse itself, but at the wider pattern surrounding it. The constellation doesn't exist as a physical cluster in space the way it appears to us. It's more like a carefully arranged illusion, a projection of stars at very different distances that happen to line up from our point of view. And yet that illusion is incredibly useful, because it gives Betelgeuse context, a frame of reference that helps us understand its place in the sky. Start with the 3 stars of Orion's belt. They sit almost perfectly in a line, easy to spot even in light-polluted skies. From there, your eyes naturally move outward, tracing the shape of the hunter. Betelgeuse sits above and to the left of the belt, marking what we interpret as the shoulder. Opposite it, lower and to the right, is Rigel, a bright blue-white star that feels like a counterpart. That pairing is worth lingering on for a moment. Betelgeuse and Rigel appear as if they belong together, balancing the figure of Orion. But in reality they are very different. Rigel is hotter, brighter in a sharper, more intense way, and much farther away than Betelgeuse. Their apparent closeness is simply a matter of perspective. From Earth, they line up. In space, they're separated by vast distances. This is one of the first quiet lessons the night sky offers. What looks connected is not always physically related. Constellations are patterns we impose, ways of organizing what we see. Betelgeuse happens to be part of one of the most recognizable of those patterns, but its story unfolds independently of the others around it. Still, those neighboring stars help us notice things we might otherwise miss. When Betelgeuse brightens or dims, it's often easier to detect by comparing it to nearby stars. You might look at Rigel, or at the belt stars, and sense that Betelgeuse is slightly more or less prominent than before. The surrounding stars act like a reference grid, allowing subtle changes to become visible. Beyond Orion itself, the sky offers even more context. Follow the line of the belt downward, and you'll find a faint, fuzzy patch of light. This is the Orion Nebula, a region where new stars are forming. It's a place of beginnings, filled with gas and dust collapsing under gravity to create new stellar systems. So within the same constellation, you have both ends of a stellar life cycle. Betelgeuse, a star nearing the end of its life, expanded and unstable. And the Orion Nebula, a region where stars are just beginning to form. It's a quiet juxtaposition, one that becomes more meaningful the longer you sit with it. Above Betelgeuse, you might notice other stars that form the upper part of Orion's outline. Some are faint, others brighter, but none quite match the warm tone of Betelgeuse. That colour continues to set it apart, even within a busy patch of sky. And if you step back a little further, letting your eyes take in a wider view, Orion itself becomes part of a larger pattern. To one side you might find Taurus, with the bright star Aldebaran, another reddish star, though smaller and closer than Betelgeuse. To the other side, perhaps Gemini with its twin stars, or Canis Major home to Sirius, the brightest star in the night sky. Each of these stars has its own properties, its own distance, its own stage of life, and yet, from Earth, they form a kind of tapestry. Betelgeuse is one thread in that tapestry, but it's a thread that stands out, both because of its colour and because of what we now know about its size and state. There's also a seasonal aspect to this. Orion is most visible in the winter months in the northern hemisphere, rising in the evening and dominating the sky for a few hours. During that time, Betelgeuse becomes a familiar sight, appearing night after night in roughly the same position, though slightly shifted as the hours pass. This regular appearance gives it a sense of reliability. Even though the star itself is changing, pulsating, shedding material, its position in the sky feels stable. It rises, it sets, it returns the next night. That rhythm can make it feel constant, even as we know it is anything but. From the southern hemisphere, Orion appears differently, oriented in another way, but still recognizable. Betelgeuse remains part of that pattern, still marking the same part of the figure, still glowing with that same reddish hue. So regardless of where you are on Earth, The star connects observers across different places. Someone looking up from one continent sees the same star as someone on another, even if the orientation of the constellation is different. The light arriving at both locations has travelled the same long journey, carrying the same information. That shared experience is part of what makes the night sky feel universal. Betelgeuse is not tied to a single place. It belongs to the sky itself, visible from many parts of the world, part of a pattern that has been recognised for centuries. There's also the matter of motion, though it's subtle. Over very long timescales, the stars do move relative to each other. Betelgeuse is not fixed in space. It has its own velocity, its own path through the galaxy. Given enough time, the shape of Orion will change, the familiar pattern gradually distorting. But this happens so slowly that it's invisible within a human lifetime. For us, Orion remains stable, a reliable reference point, a backdrop against which we can observe and compare. Returning to the present moment, though, it's worth considering how all of this influences the way we perceive Betelgeuse. On its own, it's a bright, reddish star. Within Orion, it becomes part of a recognisable figure. Within the broader sky, it becomes one element among many, its uniqueness highlighted by contrast. The surrounding stars give it scale. They allow us to see that it's not the brightest star in the sky, but it is one of the most distinctive. They help us notice its colour, its variability, its presence, and in turn Betelgeuse gives something back to that pattern. It anchors one part of Orion, adding character to the constellation. Without it, Orion would still be recognisable, but it would feel different, less balanced, less varied in colour. There's a kind of quiet relationship there. The star shapes the pattern, and the pattern shapes how we see the star. As you imagine the night sky now, with Orion rising, the belt aligned, Betelgeuse glowing at the shoulder, it becomes easier to place the star within a larger context. It's not isolated, it's part of a scene, a structure, a view that extends across the sky. And yet, knowing what we know, that this point of light represents a star of enormous size, nearing the end of its life, adds depth to that scene. It's no longer just a pattern. It becomes a layered picture, where each point of light carries its own story, its own scale, its own timeline. Betelgeuse, in particular, stands out not just because of its position, but because of what lies behind that glow. Rather than relying only on the naked eye, there comes a point where curiosity gently pushes us a little closer. Not physically, of course, because Betelgeuse remains far beyond any direct reach, but observationally. What happens when we stop seeing it as just a point of light and begin using the tools that allow us to uncover more detail? The first step in that journey is surprisingly simple. Binoculars. If you raise a pair of binoculars to the night sky and center them on Betelgeuse, the star doesn't suddenly become a visible sphere. It still appears as a point of light, but something subtle changes. The colour becomes more noticeable, a warmer, richer tone. The surrounding stars fade slightly, and Betelgeuse begins to feel more distinct, less like one of many, and more like something with its own presence. Even at this modest level, observation becomes more intentional. You begin to notice differences. The contrast between Betelgeuse and nearby stars like Rigel becomes clearer. The reddish hue stands out more strongly against the darker background. And if you return night after night, you might start to sense those gentle variations in brightness. Not dramatically, but enough to feel that the star is not entirely fixed. From there, telescopes add another layer. With a small telescope, Betelgeuse still resists revealing a sharp disk. It's simply too far away. But the light becomes steadier, more concentrated, and the colour more pronounced. Some observers describe it as having a soft glowing quality, almost as if it's slightly larger than the surrounding stars, even though this is more a trick of perception than a direct resolution of its surface. What's really happening is that your eye and brain are interpreting subtle differences in brightness and colour, giving the impression of size where none can actually be resolved at that scale. To truly observe Betelgeuse up close, astronomers have had to develop techniques far beyond traditional telescopes. One of the most important of these is interferometry, the same method we touched on earlier when discussing how its size is measured. By combining light from multiple telescopes, astronomers can achieve a resolution high enough to do something remarkable. They can actually image the surface of the star, not in the way we see planets, with sharp edges and detailed features, but as a resolved disk with variations across it. Using instruments like the Very Large Telescope, scientists have captured images of Betelgeuse that show bright and dark regions, evidence of those enormous convection cells we talked about earlier. Seeing those images for the first time can be a quiet surprise. The star is no longer an abstract concept. It becomes something with structure, with features, with a kind of texture. The surface appears uneven, mottled, changing over time as the convection cells evolve. There's also the Hubble Space Telescope, which has observed Betelgeuse in ultraviolet light. These observations reveal something different from what we see in visible light. They show the star's outer atmosphere extending far beyond its main body, a vast envelope of gas moving outward into space. In these observations, Betelgeuse looks less like a contained sphere and more like a system in motion. Gas flows outward, material escapes. The boundary between the star and space becomes blurred. It's not a clean edge, but a gradual transition shaped by temperature, pressure, and motion. More recently, observations from the James Webb Space Telescope have added yet another layer. In infrared light, astronomers can see cooler material, including dust that surrounds the star. This allows them to track how Betelgeuse loses mass, how it sheds its outer layers, and how that material spreads into the surrounding environment. These observations are particularly useful for understanding events like the Great Dimming. By looking at the star in different wavelengths, scientists can piece together what's happening. Visible light might show a drop in brightness, while infrared reveals the presence of dust that is blocking that light. Ultraviolet observations might show changes in the outer atmosphere. Each wavelength tells a different part of the story, and when combined, they create a more complete picture. There's also spectroscopy, which doesn't produce images in the traditional sense, but provides detailed information about the star's composition and motion. By splitting Betelgeuse's light into its component colours, astronomers can identify the elements present in its atmosphere and measure how fast different parts of the star are moving. This technique reveals that the surface is not still. Some regions are moving toward us, others away from us, indicating the rise and fall of material in those giant convection cells. It also shows the presence of elements like carbon and oxygen, products of the fusion processes happening inside the star. In a way, spectroscopy allows us to listen to the star. Not through sound, but through shifts in light, changes in wavelength that carry information about motion and composition. Putting all of this together, observing Betelgeuse up close becomes a layered experience. At the simplest level, you look up and see a red star. With binoculars, the colour deepens. With a telescope, the presence becomes more pronounced. With interferometry, the surface begins to resolve. With space telescopes, the atmosphere and surrounding material come into view. And with spectroscopy, the internal processes start to reveal themselves. Each step adds detail, but none of them replaces the others. The naked eye view remains just as important, because it connects you directly to the star. The advanced observations add understanding, showing what lies behind that simple point of light. There's something quietly satisfying about that progression. You don't lose the simplicity as you gain complexity. Instead, the two exist together. The star is both a distant point in the sky and a massive dynamic object with a structured surface and an extended atmosphere. Another interesting aspect of these observations is how they change over time. Betelgeuse is not static, and the images captured by telescopes reflect that. Observations taken months or years apart show differences in brightness, in surface patterns, in the distribution of surrounding material. This means that even with the most advanced tools, astronomers are not just taking a single snapshot. They are building a timeline. Each observation adds a new frame, allowing them to track changes, identify patterns, and refine their understanding of how the star behaves. There's also a sense in which these observations bring Betelgeuse closer, not physically but conceptually. Instead of being an abstract object defined by numbers, it becomes something you can visualize. A sphere with a mottled surface, a star with rising and falling currents of gas, a system surrounded by drifting clouds of material. And yet, even with all this detail, there are limits. We cannot see everything. There are processes deep inside the star that remain hidden, inferred only through indirect measurements. There are uncertainties in distance, in size, in internal structure. But those limits don't diminish the experience. If anything, they add to it. They remind us that observation is an ongoing process, that each new instrument, each new technique, reveals more, but never everything. There is always another layer, another detail waiting to be uncovered. As you imagine Betelgeuse now, not just as a point of light, but as something observed through multiple lenses, across different wavelengths with different techniques, it becomes richer, more detailed, more real. The star's surface, its atmosphere, its variability, all come into focus, not in a single image, but in a collection of observations that together form a picture. Something unusual happened not long ago, and it caught the attention of both astronomers and casual skywatchers alike. Betelgeuse, normally one of the brighter stars in Orion, began to fade. Not gradually in the way we've been describing with its regular pulsations, but noticeably enough that people who rarely looked at the sky could see the difference. For a moment it felt like something important might be happening, but to understand that event and why it matters, we need to look more closely at a part of the star we haven't fully explored yet. Not the core, not even the visible surface, but the vast extended atmosphere that surrounds Betelgeuse, reaching far beyond what we might casually think of as the star itself. Unlike smaller stars, Betelgeuse does not have a sharply defined edge. Its outer layers gradually thin out into space, forming a region where gas is still part of the star's influence, but no longer tightly bound. This extended atmosphere is enormous, stretching out to distances that can rival or exceed the radius we use when we describe the star's size. Within this region, the conditions are very different from what we might expect. The gas is cooler, less dense, and constantly moving. Material from the surface is lifted upward by convection and pulsation, carried into these outer layers where it can drift, expand, and sometimes escape entirely. This is where dust begins to form. When gas ejected from the star cools enough, atoms can combine into tiny solid particles, microscopic grains that float within the surrounding space. These particles are not like dust on Earth, but they serve a similar role in how they interact with light. They absorb it, they scatter it. And when enough of this dust gathers along our line of sight, it can change how bright the star appears to us. This brings us back to the dimming. Toward the end of 2019 and into early 2020, Betelgeuse's brightness dropped significantly, far more than its usual variability. It became noticeably fainter, enough that comparisons with nearby stars made the change obvious, even without instruments. Naturally, this raised questions. Was the star about to explode? Was this the long-anticipated supernova finally beginning? The idea spread quickly, capturing attention far beyond the astronomy community. But as observations continued, a different explanation began to emerge. The dimming was not caused by a sudden drop in the star's energy output. Instead, it was largely the result of changes in its atmosphere. A large convection cell had brought cooler material up to the surface, creating a region that emitted less light. At the same time, Betelgeuse ejected a significant amount of gas into its outer atmosphere. As this material moved outward, it cooled and formed dust. That dust drifted into our line of sight, and for a time, It partially blocked the star's light. The result was a noticeable dimming, not because the star itself had fundamentally changed, but because something had come between us and its glow. There's something quietly interesting about that. A star hundreds of millions of kilometers wide, shining across hundreds of light years, can appear dimmer simply because of a cloud of dust forming in its outer layers. It's a reminder that what we see is always influenced by the space between, not just the source itself. As the dust dispersed and moved out of the way, Betelgeuse gradually returned to its usual brightness. The event passed, but it left behind a deeper understanding of how the star behaves. It confirmed that Betelgeuse's atmosphere is not just an outer boundary, but an active region where material is constantly moving, cooling and interacting with light. It showed that mass loss is not a smooth, uniform process, but something that can happen in bursts, creating localized clouds that affect how we perceive the star. And it highlighted how closely connected the star's surface and atmosphere are. The convection cells that shape the surface can influence how material is ejected. The pulsations that expand and contract the star can push gas outward. The atmosphere in turn can reflect those changes back to us by altering the star's brightness. All of these layers are part of the same system. There's also a broader implication here. Events like the Great Dimming give astronomers a rare opportunity to study processes that are otherwise difficult to observe directly. By tracking changes in brightness, analysing spectra, and observing the star at different wavelengths, they can piece together what is happening in regions that are far too distant to explore in any physical sense. In this way, the dimming becomes more than just an interesting gutner. It becomes a source of data, a moment where the star reveals something about its structure and behaviour. At the same time, it reminds us that Betelgeuse is not static. Even though it appears steady most of the time, it is capable of noticeable changes. It can surprise us, shifting in ways that draw attention and invite closer observation. From a more reflective perspective, there's something calming about the way this unfolded. The star dimmed, people noticed, questions were asked, and then, gradually, it returned to normal. There was no sudden explosion, no dramatic end, just a temporary change followed by a return to its usual state. It's a gentle reminder that not every change signals an immediate conclusion. Sometimes, it's just part of the ongoing process. As you imagine Betelgeuse now, with its extended atmosphere, its drifting clouds of gas and dust, and its ability to dim and brighten over time, the star becomes more layered. Not just a glowing sphere, but a system with depth, an inner core, a visible surface, an extended atmosphere, and beyond that, a region where material continues to move outward, gradually becoming part of the wider galaxy. If Betelgeuse is constantly losing material, if its atmosphere extends so far, then what happens to all of that gas and dust over time? Where does it go and how does it interact with the space around the star? Numbers can feel reassuring at first. We say 600 light years and it sounds precise, almost manageable, as if we've pinned Betelgeuse down with a label we can understand. But if you pause with that number for a moment, without rushing past it, something interesting begins to happen. It starts to slip away from intuition. Because what does 600 light years really feel like? We can define it. Light travels about 300,000 kilometers every second. Multiply that by every second in a year, and then multiply again by 600. The result is a distance so large that even writing it out doesn't make it clearer. It becomes a string of digits rather than an experience. So instead of holding onto the number, it helps to approach it differently. Imagine a beam of light leaving Betelgeuse. Not in a hurry, not racing in your mind, but simply moving at its natural speed, the fastest speed anything can travel. That light begins its journey long before you were born, long before modern technology, long before many of the things we take for granted today. It travels continuously, across empty space, past clouds of gas, through regions of the galaxy where stars are forming and fading. It does not slow down, it does not pause, it simply moves forward, second after second, year after year, centuries pass, and only then does that light arrive here, reaching your eyes in the present moment. So when you look at Betelgeuse, you're not just looking across distance, you are looking across time. That realization is where human imagination begins to stretch. We are used to thinking in terms of kilometers, of hours, of distances we can travel in a day or a year. Even the scale of the solar system, while large, can still be framed in terms of spacecraft journeys, of missions that take years or decades. But hundreds of light years move beyond that. Even if you could travel at the speed of our fastest spacecraft, it would take tens of thousands of years to reach Betelgeuse. Entire civilizations would rise and fall during that journey. Languages would evolve. The starting point and the destination would no longer be the same in any meaningful human sense. So instead of trying to imagine traveling there, it can be more helpful to imagine receiving something from there. Light, information, a message carried across space, arriving quietly, without announcement. And that message is continuous. Every moment new photons from Betelgeuse are reaching Earth, each one carrying a tiny piece of information about the star. Together they form the glow we see, the colour, the brightness, the subtle variations. It's a constant connection, even across that immense distance. There's also a kind of layering to this. The light you see tonight left Betelgeuse centuries ago. The light you will see tomorrow left slightly later, but still far in the past. Each moment of observation corresponds to a different moment in the star's history, all arriving in sequence like frames of a very slow-moving film. You are, in a sense, watching the past unfold in real time. That idea can feel abstract at first, but it becomes more tangible if you let it settle. Think about events on Earth centuries ago. Now imagine that the light from those events is only just reaching some distant observer. They would be seeing our past as their present. The same is true in reverse. Betelgeuse's present is hidden from us, still travelling, still on its way. Now, this distance also shapes how we perceive the star's size. Earlier we imagined placing Betelgeuse in our solar system, letting it fill the orbits of planets. That helped translate its size into something familiar. But when it sits hundreds of light years away, that enormous size collapses into a single point of light. This is one of the most striking contrasts in astronomy. Something unimaginably large can appear incredibly small. And yet, the mind holds both ideas at once. You see a point, but you know it represents a sphere that could swallow planets. You perceive something quiet and distant, but you understand that it is active, dynamic, and vast. This duality is where imagination becomes important, not to replace the science, but to bridge the gap between what we see and what we know, because without that bridge the numbers remain abstract. 600 light years, 700 solar radii, millions of times the sun's volume. These are accurate, meaningful measurements, but they don't immediately translate into something we can feel or picture. Imagination helps soften that. It allows you to think in terms of journeys, of light travelling across centuries, of distances that stretch beyond any physical experience. It turns numbers into something closer to a narrative, a story unfolding across space and time. There's also a sense of perspective that comes with this. On Earth, distances define our daily lives. Cities, countries, continents, all separated by measurable spans. But in the context of the galaxy, those distances become small. Even the entire solar system is tiny compared to the space between stars. Betelgeuse sits within that larger framework. It is not isolated, but part of a vast structure, one star among billions in the Milky Way. Its distance from us is large, but not unusual on a galactic scale. And yet, it feels special, because we can see it, because we can study it, because it is close enough, relatively speaking, to reveal details that more distant stars cannot. This combination of accessibility and scale makes Betelgeuse a kind of anchor for our imagination. It's far enough away to challenge our sense of distance, but close enough to remain visible, to remain part of our night sky. There's something quietly comforting in that balance. We are not completely disconnected from the cosmos. We receive light, we interpret it, we build understanding. Even across hundreds of light years, there is a relationship, however indirect. And that relationship is ongoing. Every time you look at Betelgeuse, you are participating in it. You are receiving light that has travelled across centuries, interpreting it with your eyes and mind, connecting it to everything you've learned about the star. It's a simple act, but it carries a lot with it. Distance, time, energy, all condensed into a single point of light. As that idea settles, the scale of Betelgeuse begins to feel a little different. Not just large in terms of size, but large in terms of connection, of the span between where it is and where we are, of the journey its light takes to reach us. If Betelgeuse is so large, so distant, and so different from our Sun, how does it compare to other stars beyond our immediate view? Are there stars even larger, even more extreme? And where does Betelgeuse fit within that broader range of stellar giants? Right now, as you imagine looking up at Betelgeuse, it's easy to think of it as something happening in the present. A star shining, existing exactly as you see it. But the moment you slow that thought down just a little, something subtle begins to shift. Because the light reaching your eyes tonight did not leave the star tonight. It left centuries ago. Not yesterday, not last year, but hundreds of years in the past. Long before modern astronomy, long before telescopes reveal the details we now understand, long before most of the world looked anything like it does today. That light has been travelling ever since, moving steadily through space, carrying with it a snapshot of Betelgeuse at that moment in time. So when you look at the star, you're not seeing it as it is, you're seeing it as it was. This idea can feel a little abstract at first, but it becomes clearer if you think about how light behaves. Light has a finite speed, about 300,000 kilometers per second. That sounds incredibly fast, and it is, but over cosmic distances, even that speed takes time. For nearby objects like the Moon, the delay is barely noticeable. The light you see left the Moon just over a second ago. For the Sun, it's about 8 minutes. When you look at sunlight, you're seeing the Sun as it was 8 minutes in the past. But Betelgeuse is much farther away, hundreds of light years. That means the delay is not minutes, but centuries. Imagine a moment in the 14th or 15th century on Earth. Somewhere in that era, light leaves the surface of Betelgeuse. It begins its journey, moving outward in all directions. A tiny fraction of that light happens to be aimed toward where Earth will be centuries later. It travels continuously, through empty regions of space, past clouds of gas, through the quiet darkness between stars. It doesn't slow down, it doesn't change direction, it simply continues, second after second, year after year. Eventually it reaches our planet, and at that exact moment, it becomes visible to you. So the light you see tonight has been on a journey longer than any human lifetime. It has outlasted generations, crossed distances we cannot physically traverse, and arrived here as a kind of message from the past. There's something quietly profound in that, because it means that every observation of Betelgeuse is also an observation of history. Not human history, but stellar history. You are seeing a version of the star that existed long ago, preserved in light. And this is not a one-time event. It happens continuously. Each new moment, new light arrives, carrying slightly more recent information. The star you see tomorrow will be a fraction of a second newer than the one you see tonight, though still centuries behind the present state of the star itself. It's like watching a very slow broadcast. Frame by frame, moment by moment, the past unfolds. Now this also leads to an interesting thought. What is Betelgeuse doing right now? Not the version we see, but the version that exists at this very moment. Hundreds of light years away, it has continued to evolve, to pulsate, to shift, to lose material, all while its light is still on its way to us. We don't see that current state yet. We are always behind. This creates a kind of separation between knowledge and observation. We can model the star's behavior, predict its evolution, understand its processes, but the direct evidence we receive is always delayed, and that delay is unavoidable. It's built into the structure of the universe. Light takes time to travel, and that time becomes part of how we experience everything beyond our immediate surroundings. There's also a gentle implication here about the future. When Betelgeuse eventually explodes as a supernova, that event will not be visible to us immediately. The explosion will occur, and then its light will begin the long journey toward Earth. Only after centuries will it arrive, appearing suddenly in our sky as a brilliant new point of light. So even dramatic events are subject to this delay. The universe does not rush to inform us. It unfolds at its own pace, and we receive its signals when they arrive. This can feel distant, but it also creates a kind of continuity. The light we see is not random. It is connected to real events, real processes, real changes in the star. Even though we are seeing the past, that past is part of a continuous sequence leading to the present. We are simply observing it at a different point along that sequence. Another way to think about this is to imagine a timeline stretched across space. At one end is Betelgeuse as it is now. At the other end is Betelgeuse as we see it. The distance between those points is not just spatial, but temporal. The light bridges that gap, carrying information forward in time, and we are positioned at the receiving end. Every time we look up, we are stepping into that timeline, connecting with a moment that has travelled across centuries to reach us. There's also something quietly grounding about this. Even though the distances are vast, the process is simple. Light travels. We receive it. We interpret it. The complexity comes from the scale, not from the mechanism itself. This simplicity makes the experience accessible. You don't need to calculate distances or understand every detail of stellar physics to appreciate it. Just knowing that the light is old, that it has travelled, that it represents a past state of the star, is enough to change how you see it. The star becomes more than a point of light. It becomes a connection across time, and this connection is not unique to Betelgeuse. Every star you see is also in the past, though the delay varies. Some are a few years away, some thousands, some millions. The night sky, as a whole, is a mosaic of different moments, all arriving together in your present. Betelgeuse is simply one of the more noticeable examples. Because of its brightness, its colour, and its prominence in Orion, it draws attention. And once your attention is there, it becomes easier to reflect on what you're actually seeing. Not just where the star is, but when. The experience of looking at the night sky begins to change slightly. It's no longer just a view of distant objects. It becomes a view of layered time. Each star represents a different point in its own history, and all of those histories are visible at once, overlapping in the sky. Betelgeuse, with its centuries-long delay, sits comfortably within that pattern, offering a clear example of how distance and time are connected. Long before telescopes revealed its size or physics explained its behaviour, Betelgeuse was already part of human imagination. Not as a red supergiant, not as a star nearing the end of its life, but as a presence in the sky that invited interpretation. People saw it, noticed its colour, its brightness, its position in Orion, and naturally began to build stories around it. That tendency hasn't changed. Even now, with all the scientific knowledge we have, Betelgeuse continues to appear in fiction, in films, in books, in ideas about distant worlds and unknown civilizations. It sits in a space between understanding and imagination, where facts exist, but there's still room to wonder. Part of this comes from its visibility. You don't need special equipment to see Betelgeuse. It's right there in Orion, easy to find, easy to remember. That accessibility makes it a natural candidate for storytelling. A star that can be pointed out, recognized and revisited night after night becomes something familiar, and familiar things tend to find their way into stories. Its colour plays a role too. That reddish glow sets it apart. It doesn't look like most other stars. There's a warmth to it, a subtle difference that makes it feel distinct. In older traditions, that colour was sometimes associated with fire, with strength, with something alive or active. In modern fiction, it often carries a similar sense, a star that feels different, perhaps more intense, more unusual. One of the most recognisable modern appearances of Betelgeuse is in the film Betelgeuse, where the name is used, slightly altered, for a fictional character. The connection to the star is more playful than scientific, but it shows how the name itself has entered popular culture, becoming something people recognise even if they're not thinking about astronomy. In science fiction more broadly, Betelgeuse often appears as a location. Writers imagine planets orbiting it, civilizations living in its system, or events unfolding nearby. This is interesting because in reality, Betelgeuse is not an ideal candidate for long-term planetary systems as we understand them. Its size, its variability, and its stage of life make stable, habitable planets unlikely. But fiction doesn't need to follow those constraints. It uses the star as a setting, a backdrop, a place where stories can unfold. The name carries weight, a sense of distance and scale, and that's often enough. There's also something about its evolutionary stage that invites storytelling. A star nearing the end of its life, destined to explode, carries a built-in sense of tension, even though, as we've discussed, that explosion is not imminent in human terms. The idea that it will happen someday is enough to inspire narratives. What would it be like to witness that event from nearby? What kind of civilizations might exist in its system, aware of the star's fate? How would they respond? These are the kinds of questions that appear in science fiction, not because they are likely scenarios, but because they explore possibilities, stretching the imagination beyond what we can observe directly. At the same time, science has its own kind of storytelling, not fictional, but narrative in a different sense. Astronomers describe Betelgeuse's life as a sequence of stages: formation, main sequence, expansion, red supergiant phase, eventual supernova. Each stage follows from the last, connected by physical processes, but when you step back, it reads almost like a story. A beginning, a long period of stability, a transformation, and eventually an ending that leads into something new. This scientific narrative doesn't replace the older stories or the fictional ones. It exists alongside them, offering a different way of understanding the same object. There's a quiet overlap here. Ancient observers saw Betelgeuse as part of a hunter in the sky. Modern scientists see it as a massive star nearing the end of its life. Writers imagine it as the setting for distant worlds or dramatic events. Each perspective adds something. The ancient view gives it cultural meaning. The scientific view gives it physical context. The fictional view gives it imaginative space. None of these cancel the others out. Instead, they layer together, creating a richer picture. Even the way we talk about the star reflects this. We describe it as aging, as pulsating, as approaching an end. These are scientific ideas, but the language carries a hint of narrative, a way of making complex processes feel more relatable. That doesn't mean the star is alive in any human sense, but it does mean that we understand it through patterns that resemble stories, and perhaps that's unavoidable. Because when faced with something as large and distant as Betelgeuse, the mind looks for ways to connect it to experience. Stories are one of the tools we use for that, whether they are mythological, scientific, or fictional. There's also a sense in which Betelgeuse acts as a bridge between these ways of thinking. It's real, observable, measurable. You can look at it, track its brightness, study its spectrum, but it also remains distant, unreachable, open to interpretation. That combination makes it particularly well suited to imagination. A completely unknown object might be too abstract. A fully understood and nearby object might feel too constrained. Betelgeuse sits somewhere in between. We know a great deal about it, and yet there is still room to wonder. Even in modern times, new observations can shift our understanding. The Great Dimming Event, for example, briefly brought Betelgeuse into public attention, not as a fictional setting, but as a real star behaving in an unexpected way. For a while it felt like something out of a story, a bright star fading, people watching, speculating, waiting to see what would happen next. But instead of a dramatic ending, it returned to its usual brightness, reminding us that not every unusual event leads to something final. That too is part of the story. Not every change is a conclusion. Sometimes it's just a moment within a longer process. As you think about Betelgeuse now, it becomes more than just a scientific object. It becomes something that exists in multiple layers. A star in the sky, a subject of study, a source of stories, a setting for imagination, all of these at once. Not every star ends the same way, and that becomes especially clear when you begin looking at giants like Betelgeuse. We've followed its path through expansion, instability, and the gradual approach toward a supernova, but it's only one example of a broader pattern. Massive stars, the ones that grow into red supergiants, tend to share a similar fate, though the details can vary in quiet but important ways. It helps to step back and look at the bigger picture. Stars begin as clouds of gas collapsing under gravity. Over time they ignite, burn, evolve, and eventually reach an endpoint determined largely by their mass. Smaller stars like our Sun take a slow and steady path. They expand into red giants, shed their outer layers gently, and leave behind a white dwarf, a dense, cooling remnant. But massive stars follow a different route. They live faster, burn hotter, and reach their final stages much more dramatically. Betelgeuse belongs to this category, a star that began with far more mass than the Sun, and has already moved through most of its life cycle in a relatively short cosmic time. For these giants, the end is not quiet, it is explosive. Yet even within that general outcome, there are variations. Not all massive stars produce identical supernovae. The exact sequence depends on how much mass the star retains, how its internal layers are structured, and how it has evolved over time. Some stars lose a significant portion of their outer layers before they explode. Others retain more of their mass, leading to different types of supernova events. In Betelgeuse's case, the expectation is that it will undergo what astronomers call a core collapse supernova, triggered by the buildup of iron in its core. But what remains afterward can differ. In some cases, the collapsed core becomes a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. In other cases, if the remaining mass is large enough, the collapse continues further, forming a black hole. For Betelgeuse, the likely outcome is a neutron star, though there is still some uncertainty, and that uncertainty is part of what makes these stars interesting. Even with detailed models and observations, the exact fate of an individual star can be difficult to predict with absolute precision. Small differences in mass, rotation, and internal structure can lead to different outcomes. There's also the matter of what happens to the material that is expelled. When a supernova occurs, the outer layers of the star are thrown outward at incredible speeds. This material doesn't simply disappear. It spreads into the surrounding space, forming an expanding cloud known as a supernova remnant. Over time, that material mixes with the interstellar medium. The elements created inside the star, carbon, oxygen, silicon, iron, and others, become part of the galaxy. These elements are essential for the formation of planets, and ultimately for life as we know it. So the end of a giant star is also a beginning. The material that once made up Betelgeuse will not remain concentrated in a single object. It will disperse, becoming part of future stars, future planetary systems, and perhaps even future observers looking back at the sky. There's a quiet continuity in that process. The star ends, but its material continues. Another aspect to consider is the energy released during the explosion. A supernova is one of the most energetic events in the universe. For a brief period, the star can outshine entire galaxies. The energy released is immense, driving shockwaves into the surrounding space, compressing gas clouds, and sometimes triggering the formation of new stars. So the fate of giants is not isolated. Their endings influence their surroundings, shaping the structure of the galaxy in subtle but important ways. Returning to Betelgeuse, its current state gives us clues about how close it might be to that final stage. The expansion, the variability, the mass loss, all of these suggest that it has already passed through many of the earlier phases of its life. It is not a young star, and it is no longer in a stable, long-lasting stage. But it is also not at the very end. There are still processes unfolding inside it. Fusion continues in its inner layers. The balance between gravity and pressure, while delicate, is still holding. This places Betelgeuse in a kind of intermediate state, close to the end in a cosmic sense, but not immediate in a human sense. That distinction is important because it shapes how we think about the star. It is tempting to focus on the dramatic outcome, the supernova, the explosion, the transformation. But most of the star's remaining time will be spent in its current state, pulsating, shedding material, evolving gradually. The final moment when it comes will be brief. Everything leading up to it is much longer. There's also something to consider about how we will experience that event if it happens within a time frame relevant to human observation. Because of the distance, the explosion would appear as a sudden brightening in the sky, a new, intense point of light where Betelgeuse once was. It would not expand visibly in real time to the naked eye. Instead, it would shine brightly, then gradually fade over weeks and months. The details would be studied with telescopes across different wavelengths, revealing the structure of the explosion and the behavior of the expanding material. But the initial impression would be simple: a bright star where there was once a familiar one. That simplicity, combined with the depth of what is actually happening, mirrors much of what we've seen with Betelgeuse throughout this exploration. A point of light, carrying layers of complexity. As you reflect on the fate of giant stars, it becomes clear that Betelgeuse is part of a larger story. It is not unique in its destiny, though it is unique in its proximity and visibility. There are many other massive stars in the galaxy, each moving toward a similar endpoint, each contributing to the ongoing cycle of stellar evolution. And yet, Betelgeuse feels closer. Not just in distance, but in familiarity. We can see it. We can track it. We can follow its changes over time. That makes its eventual fate feel more tangible, even if it remains far in the future. Size, on its own, might seem like a simple idea. Bigger means more impressive, more powerful, more significant. That's often how we think about things on Earth. Larger mountains, larger oceans, larger structures. But when it comes to stars, and especially something like Betelgeuse, size carries a different kind of meaning. It's not just about how big something is, it's about what that size tells us. Because in the case of a star, size is a clue. It reveals how the star is living, how it has evolved, and how it will eventually end. Betelgeuse is not large by accident. It did not simply start this way and remain unchanged. Its current size is the result of a long sequence of processes, each one building on the last. Earlier in its life it was much smaller, much hotter, much more compact. The expansion into a red supergiant is something that happened over time, driven by changes deep within its core. So when we look at Betelgeuse and say that it is enormous, what we are really seeing is evidence of its stage in life. The size is telling us that the star has moved beyond its stable phase. It has exhausted the simplest fuel in its core and begun burning heavier elements. The expansion is a response to those internal changes, a visible sign of something we cannot directly observe. In that sense, size becomes a kind of language. It communicates information about the star's internal state, its history, and its future. There's also a relationship between size and energy. At first, it might seem counterintuitive. Betelgeuse is cooler at its surface than the Sun, and yet it is far more luminous overall. The reason lies in its size. Because it has such a vast surface area, Even a lower temperature can produce an enormous total output of energy. It's similar to spreading warmth over a large area. Each part may be less intense, but the total effect is still significant. Betelgeuse emits far more energy than the Sun, not because it is hotter at the surface, but because it is so much larger. This relationship between size, temperature, and luminosity is one of the key ideas in understanding stars. It shows that what we see, brightness, colour, apparent size, is connected to deeper physical properties. When astronomers measure a star's radius, they are not just measuring distance from centre to edge. They are uncovering how energy flows, how fusion operates, how the star balances itself against gravity. Another reason size matters is because it influences how the star behaves. In a smaller star, gravity holds the outer layers tightly. The surface is relatively stable, convection cells are smaller, and mass loss is minimal. In a star like Betelgeuse, the situation is very different. The outer layers are loosely bound. They can move more easily, forming those convection cells, shifting brightness, ejecting material into space. The star becomes more dynamic, more variable, more complex. So size is not just a measurement. It changes the entire character of the star. There's also the connection to lifespan. Massive stars, which tend to become large supergiants, live shorter lives than smaller stars. They burn through their fuel more quickly, moving through their stages at a faster pace. Betelgeuse, despite its enormous size, is actually much younger than the Sun in terms of total lifespan. It simply evolved more quickly. That's another way size carries meaning. It reflects not just the current state, but the rate at which the star has changed. And then there's the role of size in shaping the star's future. A star as large as Betelgeuse cannot end quietly. Its mass and structure lead to a core collapse supernova, an event that disperses its material into space. The size, combined with its mass, determines how that collapse will unfold, how much material will be ejected, and what kind of remnant will be left behind. In this way, size connects directly to destiny. It tells us not only where the star is now, but where it is going. There's also a more subtle aspect to this. Size affects how we perceive the star, both visually and conceptually. From Earth, Betelgeuse appears as a point of light, no larger than any other star. Its true size is hidden by distance. This creates a contrast between appearance and reality that is central to astronomy. We see something small, but we know it is vast. That gap between perception and understanding is where imagination comes in. It allows us to bridge the difference, to take the knowledge of size and translate it into something we can picture. Earlier, we imagined placing Betelgeuse in our solar system. That exercise was not just about scale. It was about making size meaningful, turning an abstract number into a spatial experience, showing how that size would interact with familiar distances, because without that step, size can remain abstract. Numbers alone don't always convey meaning. They need context, comparison, a way to connect them to something we already understand. Another important point is that Betelgeuse, while enormous, is not the largest star known. There are other red supergiants and hypergiants that extend even farther, pushing the limits of how large a star can become before it loses stability. This places Betelgeuse within a range, not at the absolute extreme, but still among the largest stars we can study in detail. That comparison matters. It shows that size is not a single value but part of a spectrum. Different stars reach different sizes depending on their mass, composition, and evolutionary path. Betelgeuse is one example within that broader range, and because it is relatively close, it becomes one of the most important examples. We can observe it more easily, track its changes, measure its properties with greater precision than more distant giants. So even if it is not the largest, it is one of the most accessible. There's also something quietly philosophical about this. Size, in the context of the universe, is relative. What feels enormous on Earth can be small in space. What feels distant can be nearby on a galactic scale. Betelgeuse challenges our sense of proportion. encouraging us to rethink what large really means. It expands the scale of our thinking, and in doing so, it changes how we see not just the star, but everything around it. As you hold that idea, that size is not just about magnitude, but about meaning. The story of Betelgeuse begins to feel more complete. It is large because of its past. It behaves the way it does because of that size. It will end the way it will because of that size. Everything connects back to it. Take a moment now, without rushing, and let everything settle. Not as a list of facts, not as measurements or numbers, but as a quiet impression. A reddish star in the shoulder of Orion, steady to the eye, familiar in the sky, and yet carrying within it a scale that stretches far beyond anything we encounter in everyday life. We began with a simple question: how big is Betelgeuse really? And along the way, the answer unfolded slowly, not as a single number, but as a collection of ideas. Its size compared to the Sun, its reach across the inner solar system, its surface shifting with enormous convection cells, its gentle pulsations, its dimming, its extended atmosphere drifting outward into space. Each piece added something, and together they formed a picture that is not meant to be held all at once, but to be approached gradually, the way you might approach the night sky itself. There's something important in that, because when we talk about cosmic scale, it's easy to feel overwhelmed. Distances measured in light years, sizes that swallow planets, timescales that stretch across centuries and beyond. The mind can try to grasp it all at once, and in doing so lose the sense of calm that comes from simply observing. So instead, it helps to return to something simpler. Imagine looking up again, Orion rising, the belt aligned, and Betelgeuse glowing softly in its place. No calculations, no comparisons, just the presence of the star itself, a point of light that has travelled across centuries to reach you. That alone is enough, because within that single point, everything we've explored is contained. The expansion, the turbulence, the layered fusion, the eventual supernova, all of it is there, hidden within that glow. You don't need to see it directly for it to be real. You only need to know that it exists, quietly unfolding beyond your immediate perception. There's also a kind of balance here. On one hand, Betelgeuse is immense, far beyond anything we can physically experience. On the other hand, it is visible, accessible, part of the same sky you can look at any clear night. It sits at the intersection of distance and familiarity, something both distant and present at the same time. That balance makes it easier to reflect on. It doesn't feel completely unreachable, even though it is. It doesn't feel completely abstract, even though its true nature is far removed from everyday experience. And perhaps that's why it holds attention so easily. It invites curiosity without demanding urgency. It offers scale without overwhelming the senses. It gives you something to think about, but also something to simply observe. There's no need to resolve everything. You don't need to hold every number or every process in your mind. It's enough to let the idea of it exist. To know that somewhere in that direction, hundreds of light years away, there is a star large enough to encompass the space we call home, slowly evolving, slowly changing, following its own path through time. And even that path is not something separate from everything else. The material that makes up Betelgeuse was once part of earlier stars. The material it will release in the future will become part of new ones. There's a continuity there, a cycle that connects past, present, and future in a way that doesn't require urgency or finality. It simply continues. As you sit with that thought, the question of size becomes less about measurement and more about perspective. Betelgeuse is large, yes, but its size is meaningful because of how it connects to everything around it, to the solar system we used as a reference, to the galaxy it belongs to the light that travels from it to us. Size becomes part of a relationship, not just how big something is, but how it fits into a larger picture. And within that picture, there's room for both understanding and quiet reflection. You can think about the physics, the fusion, the convection, the eventual supernova, or you can simply think about the light arriving after centuries, carrying a glimpse of something far away. Both are valid, both are part of the same experience. So as this comes to a close, there's no need for a strong ending, no final conclusion to hold on to. Just the image of the night sky, steady and familiar, and somewhere within it, Betelgeuse, still glowing, still distant, still carrying its story across space and time, arriving quietly, one moment at a time.